Over the past months, 3 separate objects, 3I Atlas, R2 Swan, and the newly detected Borisov V1, have forced astronomers into a kind of uneasy vigilance, the kind that settles deep into your chest when the universe refuses to behave the way it's supposed to. Stay with me, because what we're about to uncover stretches across tens of thousands of years, billions of miles, and 3 comets whose behaviour is rewriting the rules of how interstellar visitors are meant to act. And before we go further, make sure you're liked and subscribed, because this story is changing by the week, and you'll want to follow every new twist as it arrives. It begins with something deceptively simple: brightness. Comets brighten as they approach the sun. That part is just physics. Ice sublimates, jets erupt, dust scatters sunlight, and they bloom into something beautiful. But what 3I Atlas did was different. It didn't bloom, it detonated. 4 times brighter than expected, bright enough that even seasoned observers questioned their calibration settings, bright enough that amateur astronomers with backyard telescopes were capturing images that surpassed NASA's highly anticipated releases, and that in itself was unsettling. When a 6-inch portable telescope reveals more structural detail than multi-million-dollar space instruments, you know something unusual is happening. Not because NASA is incompetent, but because whatever 3I Atlas is doing, it's doing in ways our current tools aren't prepared to detect. The first images were innocent enough: a diffuse coma, a faint tail, the sort of thing you'd scroll past without thinking twice. But then came the plumes, gas jets tens of thousands of kilometers long, 2 Earth diameters in some cases, shooting out in discrete directional spikes. Not fuzzy, chaotic outbursts like typical comets produce, but elongated structures that seem to extend in straight, unwavering lines. One astronomer likened them to spears of light. Another, more cautious, simply called them highly unusual. The amateur images showed what NASA hadn't: 7 distinct jets, some pointing toward the sun, some away, some angled in ways no natural rotation model could comfortably explain. If a comet rotates, its jets smear into curved, spiraling forms. But these remained linear, as if something steadied them, timed them, or released them in discrete pulses. If this were the only anomaly, scientists would shrug, call it a lucky orientation, and move on. But then the colour shifted. 3I Atlas began red, an ordinary dusty red, like so many cold objects wandering through the dark. Then it turned green, then blue. Not subtly either. It was a dramatic, almost theatrical transformation. Spectral analysis hinted at diatomic carbon and possibly nickel and hydrogen emissions. Fine, plausible components, but not enough to explain the ferocity of the change, and certainly not enough to explain why the comet brightened so dramatically, while also shedding mass at a rate that some researchers estimate could reach 13% of its total body in a single phase. Comets evolve. They don't usually evolve like this. Meanwhile, NASA's press releases remained oddly muted, almost guarded. A few images, a few measured sentences, nothing more. They acknowledged uncertainties but avoided specifics, avoided the jets, avoided the sudden brightness spike, avoided the rotational inconsistencies. This silence did not go unnoticed, and it only deepened the unease when amateur astrophotographers, people with day jobs and consumer equipment, began releasing images that revealed structure NASA had not shown. In one case, a backyard rig produced a photo so detailed that researchers began tracing vectors across the jets to study their alignment. How, some wondered aloud, are amateurs outpacing NASA in visual clarity? The more interesting question, one NASA did not answer, is, what is it about 3I Atlas that seems easier to see from the ground than from orbit? But 3I Atlas wasn't alone in its strangeness. While eyes remained locked on its blue-green outbursts, another comet, R2 Swan, began displaying an equally odd behaviour, an anti-tail. For those drifting to sleep as you listen, imagine this. Comet tails always point away from the sun. Always. The solar wind pushes dust outward like a cosmic breeze, but an anti-tail points toward the sun, a narrow, defiant plume slicing back against the radiation streaming outward. Swan developed one, and not a faint suggestion of an anti-tail, a pronounced photogenic structure that amateur observers captured with almost unbelievable clarity. Whatever was erupting from its nucleus was moving fast, fast enough to push against the solar wind itself, Physical models can account for anti-tails, but they require very specific angles, speeds, and fragment geometries. Swan's anti-tail appeared early, strongly, and grew in prominence as if mimicking 3I Atlas's dramatic behaviour, rather than following classic predictions. Now imagine two comets behaving strangely. That's unusual, yes, but not unprecedented. But imagine three. Enter Borisov V1, discovered by amateur astronomer Gennady Borisov, the same name associated with the only confirmed interstellar comet before 3I Atlas. This new object arrived with the orbital signature of a long-period visitor, its eccentricity 1.1095. In plain language, that means it is nearly hyperbolic, riding the razor-thin line between being bound to the Sun and escaping forever. Its inclination, 113 degrees, a retrograde orbit tilted sharply against the plane of the planets. Objects from the Kuiper belt do not enter at such angles. This orbit resembles something from the Oort cloud, or from beyond. When observations came in, astronomers noticed something odd. Borisov V1 had almost no dust structure at all. No clear tail, no broad coma, just a dense, compact nucleus streaking inward on a path that, by all appearances, belongs to something that last visited tens of thousands of years ago. Its estimated orbital period? 69,000 years. A return cadence so long that when it last swept through, Earth was locked in ice and early humans were carving tools from bone and walking alongside mammoths, with 3I Atlas displaying jets that look suspiciously organised, with Swan producing an anti-tail strong enough to defy solar wind, with Borisov V1 arriving on a retrograde path so tilted it nearly qualifies as interstellar. Astronomers began to ask a question they rarely voice publicly. Why are so many comets behaving strangely at the same time? Some point to coincidence, others to improved detection methods. But those who study celestial mechanics understand how rare it is to see such dramatic anomalies clustered in a single observational window, especially now, when the Sun sits near a solar maximum, firing CMEs and flares with increased frequency. During one particularly striking moment, 3I Atlas aligned with the Sun and Earth in a superior conjunction, and the Sun erupted with a major coronal mass ejection almost exactly during the event. Was it coincidence? Probably, but the timing felt unsettlingly precise. A cosmic choreography we weren't meant to notice, but did. And while NASA maintains caution, and rightly so, there's an undeniable pattern emerging. These objects are not behaving like the quiet, predictable wanderers we teach in textbooks. They are brightening unexpectedly, jetting material in colossal, linear beams, changing colour in days instead of months, producing anti-tails that defy simple models, arriving on orbits so extreme they brush against interstellar classification. And maybe the most curious part of all, it's the amateurs showing us the clearest views. In basements, backyards, and mountaintops, they point their telescopes upward and capture images NASA cannot, or chooses not to, release in detail. Their photos reveal jets, fragmentation lines, evolving debris fans, and structural asymmetries that suggest these comets are not simply thawing. They're changing, rapidly, dramatically, possibly catastrophically. And if that's the case, then a larger question emerges in the dark behind it, a question many hesitate to ask aloud. What is happening across the comet population of our solar system right now? Is this a coincidence of timing, a response to solar conditions, a cascade of unrelated fragmentation events, or the earlier signs of something we don't yet understand, something unfolding on scales far grander than our science has prepared us for? Whatever the answer, this is only the beginning. And as the data continues to sharpen, the story these comets are telling us is becoming impossible to ignore. If you've been following the sky lately, and if you're here, you probably have, you may have felt it too. That quiet shift, that sense that something in the solar system has begun to stir. Not in a dramatic Hollywood way, not in flashes of light or sudden disasters, but in subtle patterns, in synchronized anomalies, in the strange behavior of objects we once considered mundane. Comets are supposed to be predictable in their unpredictability. Chaotic, yes, but within boundaries. Beautiful, yes, but in familiar ways. Yet 3I Atlas, Swan, and Borisov V1 are behaving less like isolated curiosities and more like participants in an unfolding story whose script we haven't yet read. And the deeper astronomers look, the more the pieces begin to align. They noticed, for example, how amateur telescopes, small, unassuming, often transported in the trunk of a car, were capturing details NASA's high-budget instruments did not disclose. Long, coherent jets etched against the dark, colour gradients spreading across the coma in waves, shadows and fissures hinting at internal fractures or vents, the kind of imagery that shouldn't be possible from ground-based equipment under city lights, and yet, there it was, sharp, textured, undeniable. Night after night, more images appeared from observers across Europe, North America, South America. It was as if the cosmos had decided that the public, not the institutions, should be the first to witness what was happening. But images were just the beginning. As 3i Atlas continued its journey, astronomers tracked its rotation. At first, the data suggested a 16-hour spin, normal enough. But the behaviour of those massive jets didn't match that rotation pattern. If 3i Atlas were truly tumbling every 16 hours, the jets should have twisted, smeared, curved in elegant arcs through the coma. Instead, they held straight, like rigid beams extending from a lighthouse. Some pointed toward the sun, others away, others sideways, as if coordinated by an invisible metronome. And then came the estimates. For jets of that length to exist, 3i Atlas would have had to eject material equal to a staggering fraction of its total mass, 13%, in one phase. That number alone stopped researchers cold. Comets don't casually shed double-digit percentages of their mass in clean, directional bursts. That's the kind of thing you expect from a structural breakup, a catastrophic venting, a terminal stage. Yet 3i Atlas did not fragment. It did not dissipate. Instead, it tightened its coma, sharpened its features, as if it had expelled what it needed to expel and now moved with renewed purpose. Some scientists whispered the phrase non-gravitational acceleration, the same term used when outgassing pushes a body in ways gravity alone cannot explain. But as with 3i Atlas's sudden brightening, the standard explanations no longer sat comfortably. Meanwhile, R2 Swan was undergoing its own transformation. Its anti-tail, thin, luminous, defiant, continued to stretch toward the sun, a behaviour that in astronomical terms borders on rebellion. For an anti-tail to form, particles must be ejected at high speed, overcoming both solar radiation and solar wind. The configuration has to be perfect, the geometry has to cooperate, and the comet must expel material with an almost explosive force. Swan fit those criteria unnervingly well, producing images so striking they circulated among astronomers with equal parts excitement and unease. The anti-tail was more than a curiosity. It was a sign that the comet was undergoing internal changes at a scale not yet fully understood. Then came the new comet, Borisov V1, adding another thread to an already tangled tapestry. It streaked down toward the sun on a path so tilted, so retrograde, so eccentric, that at first glance it resembled an interstellar intruder. Nearly hyperbolic. Period of 69,000 years. No pronounced coma, no tail, just a compact, dense core travelling through space like a stone flung from the deep cold. Long-period comets do this, yes. But the absence of a dust envelope this close to the sun raised new questions. Was it volatile, poor, dormant, or simply ancient to a degree that its structure no longer followed patterns gleaned from younger comets? Some researchers pointed to the Oort cloud, that mysterious halo of icy remnants encasing the solar system. Objects that originate there move on orbits unlike anything from the Kuiper belt, wildly tilted, deeply elongated, almost theatrical in their extremes. But even so, Borisov V1 stood out. Not for what it displayed, but for what it refused to display. No tail, no visible outgassing, no dramatic brightening as it passed perihelion. Just silence. A ghost of a comet moving with the dignity of something older than recorded human history. There's a strange truth in astronomy. Sometimes the loudest signal is the one that refuses to speak. And so, in the span of months, astronomers found themselves confronted not with one anomaly, but three. A trio of visitors each bending the rules in different ways. A comet brightening too fast and shedding mass in linear beams. A comet thrusting material toward the sun in a rare and photogenic display. and another comet moving with the quiet confidence of a relic returning from a 70,000-year slumber. Patterns began to emerge, not causal ones, no responsible scientist would say that, but resonances, echoes, rhymes. For instance, consider the timing. All three comets revealed their oddities during a period of elevated solar activity: flares, coronal mass ejections, magnetic turbulence. The sun, in a sense, was speaking loudly, and the comets seemed to be listening. When 3I Atlas aligned with Earth and the Sun in a superior conjunction, the Sun erupted with a major CME almost precisely during the window of alignment. Correlation doesn't imply causation, but neither does coincidence erase curiosity. The conjunction also brought another surprise: a temporary captured satellite near Earth, a small body drifting close, enough to be nicknamed a second moon. For a brief moment in cosmic terms, Earth found itself with company. The timing overlapped with 3I Atlas's alignment. Again, correlation, not explanation. But for astronomers trained to see patterns in the noise, it was yet another puzzle piece falling onto the table, even if no picture had yet emerged. And then there was the matter of data, specifically who was providing it. NASA released images, yes, but the detail, the drama, the structural clarity, those came from individuals standing in backyards, in deserts, on hilltops, using equipment that, in the grand scheme of space science, is charmingly modest. They stacked exposures, pushed contrast curves, and revealed plumes so large they dwarfed Earth itself. They exposed vents that stretched tens of thousands of kilometers, captured fans of dust curling in luminous arcs, recorded color shifts that spoke of unusual chemistry. Some scientists expressed frustration, not with the amateurs, not at all, but with the silence from official channels. Why no commentary on the jets? Why no discussion of the brightening? Why so little acknowledgement of the anti-tail? The data existed, the anomalies were real, and the public, curious, informed, increasingly skilled, was piecing the story together whether NASA offered guidance or not. Meanwhile, others urge caution. Anomalies happen. Comets are complex. The universe is under no obligation to mirror our expectations, yet even they had to admit, seeing so many rare behaviors clustered in such a narrow observation window is something worth paying attention to, not to sensationalize, not to speculate wildly, but to listen, to observe, to admit that we may be entering a period of discovery where comets, often ignored until they become bright enough to photograph, begin revealing secrets about the early solar system, about interstellar visitors, about the hidden architecture of cosmic debris. And for those drifting into sleep now, let this settle over you like a soft blanket. The universe is not static. It is alive with motion, with transformation, with processes playing out on scales too vast for a single lifetime. These comets are not intruders. They are messengers. Some are ancient, some are interstellar, some are breaking apart, some are surprising us with their resilience. But all of them, every last one, is reminding us that our solar system is not a quiet neighborhood. It is a dynamic, breathing environment where ice becomes gas, color becomes signal, silence becomes mystery, and sometimes, to our astonishment, small telescopes reveal truths that giant machines overlook. The story isn't finished, not even close, and as more data arrives, the universe may be preparing to show us something we were never looking for, but now can no longer ignore. As the weeks passed, astronomers began reviewing not just the individual data from each comet, but the broader context, how these objects fit into the dynamic architecture of the solar system. Because if there's one thing the cosmos teaches again and again, it's that nothing happens in isolation. An object brightens here, another sheds mass there, a third arrives on an impossible orbit. But when these anomalies cluster in time, when they form a pattern that stretches across millions of kilometers of interplanetary space, even the most cautious scientists begin to lean forward, sensing a shift in the narrative. One of the first clues came from observing how 3I Atlas interacted with the solar wind. Normally, a comet's tail is pushed backward, stretched away from the sun in a long luminous stream. But 3I Atlas's jets were so forceful, so voluminous, that at moments they seemed to deflect the tail's orientation. Instead of being shaped by the solar wind, parts of the coma appeared to resist it, almost like a sail billowing against a storm. This behaviour fascinated researchers because it hinted at internal pressures far greater than standard sublimation could produce. Something deep inside 3I Atlas was forcing gas outward with immense speed, carving out linear plumes that cut through space like luminous arrows. At the same time, the solar activity continued to intensify. Flares burst from the sun's surface, twisting magnetic fields into snarling loops of plasma. Charged particles raced outward, washing across the heliosphere, interacting with planetary magnetospheres and cometary comas alike. It created a kind of cosmic laboratory, one where 3I Atlas, Swan, and Borisov each reacted to the solar environment in their own distinctive ways, and it became increasingly clear that these reactions were extreme outliers, pushing the boundaries of what scientists thought comets could endure without fragmenting entirely. But perhaps the most intriguing development came when observers noticed a strange synchronization between the comets and the Sun's behaviour. During one of 3I Atlas's brightest phases, the Sun emitted a strong coronal mass ejection. The timing was uncanny. While the scientific consensus remains that these events are unrelated, the coincidence lingered in conversations, in late-night emails between researchers, in quiet remarks made after telescopes were powered down for the night. Because even if the events were not causally connected, they were aesthetically connected. Two celestial bodies erupting with energy in the same window of time, each revealing their internal complexity. As Swan approached perihelion, its anti-tail grew sharper, more pronounced. It carved a narrow beam toward the sun, a surreal inversion of the normal cometary architecture. The anti-tail almost looked like a dagger pointing inward, defying everything an introductory astronomy textbook would teach. As more images arrived, astronomers noticed something even stranger. The particle composition in the anti-tail appeared finer, more consistent, as if the comet were releasing material in a highly uniform way. Normally, dust emitted by comets varies in size, shape, and reflectivity, creating a gradient of brightness. But Swan's anti-tail seemed unnaturally clean, almost engineered in its consistency. No one claimed this publicly, of course, but in private discussions, researchers wondered whether Swan had undergone a structural resurfacing event, some internal collapse or reconfiguration that exposed a fresh, volatile layer with unique chemistry. Meanwhile, Borisov V1 continued its silent descent, stubbornly refusing to behave like a typical comet. Its coma remained faint, almost reluctant. Its motion remained razor-straight, the kind of orbit that feels less like a meandering wanderer and more like something launched, not by intention, necessarily, but by a distant gravitational event tens of thousands of years ago, perhaps the passing of a star, perhaps a collision in the outer Oort cloud, perhaps something we have no name for yet. The object behaved with a solemn precision, as if it carried with it the quiet memory of its long journey. And then came the turning point, when astronomers began to overlay the orbital paths of 3I Atlas, Swan and Borisov V1 onto a single solar system model. A subtle pattern emerged. The comets were not converging, not heading toward the same point in space, but they were moving through regions of the solar system heavily influenced by the sun's magnetic architecture. It was as if they were tracing the edges of invisible currents, responding to subtle forces that elude direct measurement. This realization did not solve the mystery, but it reframed it. The universe wasn't sending individual anomalies. It was revealing a larger, interconnected system of behavior, one that becomes visible only when multiple objects move through it simultaneously. Amateurs played an unexpected role in uncovering this pattern. One observer in Arizona captured a time-lapse sequence of 3I Atlas over 6 nights. At first glance, it looked like any other comet drift. But when he compressed the frames into a continuous video, a subtle pulsing effect appeared in the coma, a rhythmic brightening and dimming that occurred in intervals of roughly 12 hours. Was it rotation? Maybe. Was it interaction with solar flux? Possibly. But the regularity of the pulse caught researchers off guard. Comets can flicker, they can flare, but they don't typically pulse like a heartbeat. Another amateur observer in Spain recorded Swan with a deep sky hydrogen filter. The resulting image showed a faint halo around the anti-tail, a diffuse envelope glowing like a torch inside a fog. The structure seemed to twist, not because the comet was rotating, but because the solar wind in that region was unusually turbulent. That turbulence, interacting with Swan's strangely uniform dust stream, created patterns that looked more like fluid dynamics than celestial mechanics. And then, from a mountaintop in Chile, a third observer captured Borisov V1 with such clarity that researchers could directly measure its rate of motion across the sky. What they found startled them. Borisov was slowing slightly more than expected. Not dramatically, not enough to suggest an active process, but enough to raise questions. Was the object shedding a thin veil of dust we couldn't detect? Was solar radiation pressure affecting it more than assumed? Or was the object interacting with an unusual region of the sun's magnetic field? The answers remained elusive, but the questions kept multiplying. One astrophysicist described the situation like this. It's not that the comets are communicating with each other, it's that they're all responding to a solar system we don't fully understand. The idea struck a chord, because the more astronomers examined the data, the more they realized how incomplete our models of the solar environment truly are. We tend to think of space as empty, as a vacuum, but it isn't. It's a sea of plasma, radiation, magnetic fields, charged particles, invisible currents that stretch millions of kilometers. And objects passing through that environment, especially icy bodies with fragile structures, respond in ways that can look chaotic or orchestrated, or in rare cases, eerily synchronized. Yet despite the scientific explanations, a quieter, more unsettling question lingered at the edge of every discussion. Why now? Why this cluster of anomalies in such a short period of time? Why the sudden visibility of extreme features that rarely appear so dramatically? Some pointed to coincidence, others to increased human observation, more telescopes, more imaging, more algorithms scanning the night sky. But a few wondered whether we're simply paying closer attention at the right moment in cosmic history, catching glimpses of processes that have always been there, but were too subtle to notice until now. Because here's the truth. Comets are messengers from deep time. They carry the chemical signatures of the early solar system. They carry stories from eras before Earth cooled, before the moon formed, before the sun settled into its stable glow. When they behave strangely, the universe is not malfunctioning. It's communicating in the only way vast ancient phenomena can, through patterns written in ice and dust, through outbursts and silences, through orbits measured in millennia. And as 3i Atlas continues to brighten, as Swan sharpens its anti-tail, as Borisov V1 glides inward on its near-hyperbolic arc, astronomers are realizing something essential. We are not watching isolated events. We are witnessing a moment of cosmic revelation, a convergence of anomalies that will force us to refine our models, rethink our assumptions, and reconsider what we thought we knew about the quiet wanderers at the edge of the solar system. Because sometimes the universe whispers, and sometimes it begins to speak. And the comets, these ancient icy travellers, may be telling us something we were never supposed to miss. What began as a collection of curious data points was now evolving into something larger, something that felt less like a series of coincidences and more like a chapter unfolding in the solar system's ongoing story. Astronomers were not ready to announce anything unusual, not publicly, but the private conversations, those late-night exchanges between observatories, the quiet messages passed between researchers who had spent decades studying these icy wanderers, carried a tone that hadn't been heard in years. Not panic, not fear, something else. Something more reflective, a sense that the universe was tugging gently at the corner of a curtain, hinting at a structure behind the familiar. It was during this period that cometary physicists began examining the internal behavior of the comets, rather than just the external displays. 3i Atlas's pulse, that slow 12-hour flicker captured unintentionally by an amateur time-lapse, became a subject of intense interest. Pulsing is not unheard of, but it is usually tied to rotational illumination, sunlight sweeping across the surface in cycles. Yet the pulse in 3i Atlas did not align perfectly with any single rotation model. Instead, it seemed to reflect internal cycling, as though heat or volatile gas pockets deep within the nucleus were rhythmically building pressure and releasing it in controlled intervals. This interpretation, even in the most conservative framing, raised eyebrows. Comets typically vent when they must, not when they choose. They respond to sunlight, not internal timers. Swan had its own mystery brewing beneath its icy exterior. As astronomers applied advanced filtering techniques to its images, a strange spiral-like pattern appeared faintly within the halo surrounding the anti-tail. The pattern wasn't a perfect spiral, nothing in space ever is, but it suggested a rotational shedding process, a kind of corkscrew dispersal of ultra-fine particles. It was delicate, almost elegant, and unlike anything commonly observed in short-period comets. And as Swan approached the Sun, the pattern intensified, becoming more coherent, more pronounced, like a signal being amplified. Some researchers proposed a layered nucleus structure, with pockets of volatiles erupting from beneath rotating plates of crust. Others believed the spiral hinted at a deeper instability, the kind that precedes fragmentation. Yet Swan did not fragment. It held together, defying predictions, even as it shed material in these surreal sculpted forms. And then came a subtle shift in Borisov V1, a change so slight that only the most patient observers caught it. For weeks the comet had travelled on a clean, unwavering arc, its coma faint, its signature almost too subtle for most telescopes. But as it crossed into a region of space dense with solar magnetic flux, its apparent velocity began to fluctuate ever so slightly. Not enough for a press release, not enough for a headline, but enough for experienced astronomers to notice a whisper of irregularity in the light curve. The comet brightened by a fraction, then dimmed, then brightened again. Not dramatically, just enough to break the monotony of its silence. Was it venting after all, or interacting with something we have not mapped? The answer never arrived, but the question refused to leave. As these three comets played out their dramas across the night sky, discussion shifted to something more fundamental, the architecture of the Sun's outer magnetic environment. For decades, heliophysicists have mapped the broad strokes of the heliosphere, but the fine structure, the filaments of magnetic tension, the braided fields, the pockets of plasma density, remains poorly understood. And in moments like this, the solar system has a way of revealing its hidden scaffolding. A comet with strong jets traces the contours of magnetic tension. A dust-rich anti-tail becomes a canvas for solar wind turbulence. A dormant relic drifting inward becomes a probe of the heliosphere's deepest regions. One researcher compared the three comets to ink dropped into water. The patterns they create reveal the currents that were invisible before. This analogy spread quickly among observatories, gaining traction not because it was poetic, but because it felt accurate. The comets weren't strange for their own sake. They were responding to environmental conditions that, until now, we simply weren't able to see. And it was precisely at this moment, when astronomers were beginning to understand that the anomalies might be clues rather than exceptions, that a new wave of amateur images arrived, revealing yet another layer. A photographer in rural Australia managed to capture 3i Atlas and Swan on the same night, under unusually stable atmospheric conditions. When he aligned his images, something caught his attention. The angle of 3i Atlas's longest jet and the orientation of Swan's anti-tail both loosely matched a particular band of solar magnetic flux visible in solar observatory data from the same week. Completely different objects, millions of kilometers apart, responding in parallel ways to the same invisible force. It was subtle, it required careful analysis, but it was there, and in that moment the narrative shifted from three comets behaving oddly to the solar system itself revealing a deeper pattern. The comets weren't the anomaly, our understanding of the environment was, but perhaps the most profound realization grew quietly in the background. These icy bodies, ancient, fragile, drifting for millennia, might be the most sensitive sensors the solar system possesses. They are vulnerable to changes in radiation, heat, gravity, plasma, magnetism. They are not resilient like planets or structured like asteroids. They are reactive, expressive, delicate. When something is happening in the solar system, something subtle, something distributed over immense scales, comets are the first to reveal it. This idea fascinated the scientific community. It also carried a weight that's hard to describe. Because if comets are sensors, and three of them are exhibiting extreme, synchronized responses, then the solar system is not as quiet as we once believed. And for those quietly drifting towards sleep, consider this. The solar system has rhythms, long cycles, invisible tides, deep currents. Some operate on scales of years, others on centuries, others still on tens of thousands of years. Borisov V1, with its 69,000-year orbit, may be responding to forces that last affected it before the first human civilizations formed. 3I Atlas, erupting in linear jets that resemble cosmic lighthouses, may be tracing the magnetic field lines of a solar cycle we barely understand. Swan, with its elegant anti-tail, may be illustrating how dust behaves in regions of solar turbulence we've never directly mapped. These are not coincidences, they are conversations between comet and star, between ice and radiation, between ancient trajectories and present-day energies, between what we see and what we have yet to comprehend. And as more telescopes, both amateur and professional, turn their gaze upward, the story continues to evolve. New images arrive nightly, new measurements deepen the mystery, new behaviours emerge, some subtle, some dramatic, but all pointing to the same conclusion. We are witnessing a rare alignment of cosmic conditions, and comets, for the first time in decades, are becoming the narrators of the solar system's unfolding tale. Because sometimes, the smallest, quietest wanderers carry the loudest truths, and as their tales sweep across the darkness, they're telling us, pay attention, something is shifting out here. Not dangerous, not catastrophic, but meaningful, and unmistakably alive. As winter deepened across the northern hemisphere and clouds rolled over observatories, the universe continued its quiet work above the haze. The comets drifted on, 3I Atlas shedding faint pulses of gas into the void, Swan sharpening and thinning its sun-facing spear, Borisov V1 descending with the steady patience of a traveller who has known only darkness for longer than humanity has existed. And even when telescopes were shuttered by weather, astronomers couldn't shake the growing feeling that these objects were not independent curiosities. They were threads, and the solar system, vast, dynamic, and deeply interconnected, was weaving those threads into something we were only beginning to recognize. For decades, we've spoken of the solar system as if it were a static mechanical structure, a predictable clockwork of planets circling a stable star. But anyone who has studied the sun knows how false that simplicity is. The sun breathes, it pulses with magnetic storms and long-term cycles. It sheds material, draws in charged particles, twists its magnetic field into knots that snap, crack, and reform. And as those changes ripple outward, everything feels the effects. Earth's ionosphere, Jupiter's auroras, Saturn's rings, and yes, comets drifting silently near the heliosphere's edge. 3I Atlas was the first to reveal this in ways we couldn't ignore. As the sun entered its active phase, 3I Atlas's jets strengthened, fan-like structures blossoming outward with a precision that defied randomness. When researchers mapped the direction of those jets against solar magnetic field models, some discovered an uncanny alignment. Not perfect. Nothing in space is, but suggestive. The jets weren't merely venting, they were responding, as if 3I Atlas were grazing the tops of magnetic waves rising from the sun, like a hand skimming the surface of an ocean. Swan's anti-tail, once an oddity, soon began behaving like a diagnostic instrument. The turbulence within the anti-tail corresponded closely with solar wind data, CMEs, minor flares, shifts in magnetic polarity. Every time the sun stirred, Swan reacted. Not explosively, not dramatically, but consistently. It became clear that Swan wasn't simply shedding dust. It was revealing the texture of a region of space that science rarely gets to observe directly. Think of it as a windsock placed in a gale. Except this windsock was an icy relic from the outer edges of the solar system, responding to every change in solar breath. Even Borisov V1, the silent one, the comet that resisted theatrics, began participating in its own way. As it crossed a region predicted to contain a braided magnetic filament, its motion shifted subtly, as though passing through a current. Astronomers debated this fiercely. Was it the measurement error? Was the faint brightening the result of a small, unnoticed outburst? Or was Borisov's icy surface reacting to solar forces in ways we had never seen up close? The debate was never resolved. But the timing once again aligned with solar data that had been collected during the same period. A filament, a faint brightening, a whisper of acceleration. Nothing conclusive, everything intriguing. These observations collided with another growing realization. The inner solar system itself was changing. Not in a catastrophic way, not in a way anyone should fear, but in a way that indicated the Sun was entering a more turbulent phase. Solar maximums are part of a natural cycle, but everyone is different, some mild, some violent, some oddly quiet. This one, researchers suspected, might be transitional, a shift not just in intensity, but in character, a shift that comets, with their fragile structures and sensitivity to environmental stimulus, were detecting long before our instruments fully registered it. Astronomers began revisiting old data from past comets, Hyakutake, Hale-Bopp, West, Ezon. They compared brightness, curves, gas compositions, tail geometries, and while each had its peculiarities, none displayed the specific combination unfolding now. Synchronized brightness anomalies, coordinated structural changes, color transitions, antitails forming early and strongly, long jets remaining linear beyond rotational expectations. The more data they compared, the clearer the conclusion became. The current wave of comets was behaving in ways that suggested a shared environmental cause. But the environment was not just solar, it extended deeper, farther, into realms humanity rarely contemplates. The boundary of the heliosphere, the vast bubble inflated by the solar wind, was undergoing subtle distortions. Spacecraft like Voyager had hinted for years that the heliosphere's shape was not perfectly round. It was wrinkled, tilted, pressured by the interstellar medium, and as the Sun's magnetic field shifted, those boundaries shifted with it, creating ripples that propagated inward. Most objects never feel those changes, but comets, especially those on elongated orbits, pass through regions of space that act like seams in the cosmic fabric. They reveal changes long before planets do. This wider structural shift, subtle as it was, could explain why these comets were behaving almost like synchronized instruments in a symphony we did not know we were listening to. Still, observations alone were not enough. Something deeper tugged at astronomers, something psychological, something philosophical, especially among those who had studied comets their entire careers. Because comets, more than any other objects in the solar system, carry with them a sense of ancientness. They are remnants of the solar system's birth, frozen archives of chemical compositions from an era before the planets fully formed. When they act strangely, it's not merely a scientific anomaly, it's a reminder that the solar system is not finished, that it continues to evolve, that forces larger than human history are still shaping the environment we inhabit. This realization weighed heavily on researchers, especially as more amateur images revealed new patterns. One set of photographs captured 3I Atlas's jets splitting, forking like branches of a tree, creating symmetrical patterns in ways that seemed orchestrated. Another revealed Swan's anti-tail bending gently, like a reed in a river current, reacting coherently to solar wind changes. And a particularly stunning image from a Chilean mountaintop showed Borisov V1's faint halo elongating briefly, just enough to suggest internal stirring. None of these observations, individually, were unprecedented, but the clustering, the cadence, the timing, the symmetry gave them the weight of significance. It wasn't long before a new theory began circulating quietly among heliophysicists and dynamical modelers. Not a formal theory, not a published one, just a whisper shared cautiously in conference halls. What if we are witnessing the solar system transitioning into a different magnetic mode? Not a catastrophic mode, not a dangerous one, just different. A new alignment of magnetic fields, a reconfiguration of heliospheric currents, a subtle restructuring of the Sun's long-term cycle. If such a transition were happening, comets would be the first to tell us. Their jets would stiffen, their tails would warp, their nuclei would heat unevenly, their colours would shift, their orbits would reveal minute accelerations, their behaviour would rhyme across millions of kilometres, exactly as 3I Atlas, Swan, and Borisov V1 were doing now. And yet, even as these theories circulated behind closed doors, another, quieter thought crept into the minds of those who watched the sky night after night. What if this isn't the first time the solar system has done this? What if this is simply a cycle we've never lived long enough to observe before? Consider Borisov V1's 69,000-year orbit. That means the last time it passed through the inner solar system, Earth was locked in ice, and humanity was still sculpting the earliest tools. It would have seen a different sun, one at a different point in its deep magnetic cycles. It would have reacted to different conditions then, just as it reacts to the Sun's environment now. 3I Atlas and Swan, though younger in orbital history, are responding to the same stage of solar evolution, each in their way, each marking the changes with jets, anti-tails, and subtle pulses. Comets are not the mystery, they are the messengers, and as their behaviour grows more complex, more expressive, astronomers understand the truth with tingling clarity. We are living through a moment of cosmic transition. Not dangerous, not alarming, but extraordinary in its rarity. The solar system is adjusting itself, breathing differently, speaking more loudly, and comets, these fragile pearls of the outer dark, are translating that message into light. What comes next is something no one yet knows, but it's becoming impossible to look at the night sky without feeling that the universe is preparing to show us something it has not revealed in a very, very long time. As astronomers traced these shifting patterns through the early months of observation, something else began revealing itself, something quieter than the brightness curves, subtler than the jet morphologies, but more consequential than either. It was the background, the cosmic backdrop behind the comets, the fabric of charged particles and magnetic turbulence through which they drifted. The more scientists examined this backdrop, the more they realized that it was not static at all. It was evolving, thickening in places, thinning in others, as if the solar system's invisible architecture were breathing with a deeper rhythm. And as these changes unfolded, the comets responded with what looked almost like personality. 3I Atlas, ever dramatic, reacted with sudden, bright pulses and stiffening jets that traced the contours of magnetic shifts. Swan, with its refined dust streams and its elegant anti-tail, began to twist slightly, as though the fine particles were being coaxed by forces we had not yet learned to interpret. And Borisov V1, the quiet one, offered faint but consistent hints of internal stirring whenever it crossed boundaries defined only in models and predictions. It became clear that these objects were not merely passive wanderers. They were interacting with the solar system the same way seeds riding an ocean current respond to turbulence, temperature gradients, salinity differences. They were revealing what the planets, locked in their stable orbits, could not show us. Comets move through everything. They cross regions of compressed magnetic field. They skirt the edges of the heliopause. They drift through strands of interplanetary dust, pockets of plasma, corridors of gravitational influence. And in doing so, their surfaces, fragile, volatile, ancient, respond with clarity. It was during a long night at a mountaintop observatory in Hawaii that one astronomer noticed something in the time series data for 3I Atlas, a deepening modulation in brightness that seemed to correspond with a rotational mode shift. Comets rotate irregularly, but when internal pressures build and release in repeating intervals, the rotational period can appear to drift. In 3I Atlas's case, the drift wasn't random. It trended in one direction for days, then stabilized abruptly, as though the comet had settled into a more energetically favorable orientation. Comets are not alive, but their physics can make them appear as if they are choosing. Swan 2 revealed a subtle choice of its own. One researcher analysing infrared data noticed that the thermal signature of its nucleus fluctuated in a way that suggested not random venting, but localised heating. Heating that migrated slowly across the surface. If sunlight alone were responsible, the heating would simply track the comet's rotation. But Swan's thermal bloom shifted irregularly, like a glow passing beneath a pane of frosted glass. This behaviour hinted at an internal structure more complex than expected, possibly cavities shifting heat through sublimation cycles, possibly layered ices responding unevenly to solar input. Even Borisov V1 showed signs of complexity. When modelers projected its path backward through thousands of years, they found a curious alignment. At its last perihelion, roughly 69,000 years ago, the Sun was in a different magnetic epoch, slightly weaker, slightly cooler, slightly more quiescent. The comet's faintness today may be a relic of that era, a cryogenic signature preserved across ice ages and interstellar cold. But as it descended into a more turbulent solar environment, it responded, however faintly. This, more than anything, caught the attention of scientists studying long-term solar cycles. Borisov was a data point that spanned millennia. The idea that these three comets were providing a multi-layered portrait of the solar system's deeper rhythms began to feel less speculative and more like a quiet truth. But the truth carried weight, a kind of sobering awe. humanity has existed for only a sliver of astronomical time. Most cosmic cycles extend far beyond a single lifetime, far beyond a single civilization. To witness a transitional phase, to be present for it, to record it, to feel it unfolding in the behaviour of ancient ice, was extraordinary in a way that defied language. And yet, despite the wonder, there was unease too. It wasn't fear. Nothing about the comets threatened Earth. Their paths were distant. Their behaviours, though strange, carried no danger. The unease came from the realisation that the universe is not the stable, predictable place we imagined. It shifts, it breathes, it enters phases we do not yet understand. And the fact that 3 comets, each unique, each ancient, each on completely different trajectories, were responding at the same time suggested that the solar system was entering one of those phases. The first hints of this idea began spreading through scientific forums. Not publicly, not in press releases or conferences, but in quiet technical discussions that drifted into more philosophical territory. A heliophysicist in Sweden wrote that the current solar environment resembled the early stages of a magnetic reconfiguration. A plasma physicist in Japan compared the data to rare intervals in fusion experiments when multiple parameters shift simultaneously. A dynamicist in Germany suggested that the current behaviour might be a precursor to a long-term change in the Sun's outer field. None of these ideas were definitive, but the conversations all pointed in the same direction. Something large, something subtle, something multi-decadal or even multi-century in scale was beginning. And for the first time, astronomers realised that they were not observing a series of anomalies. They were witnessing a transition. One observer in Argentina captured Swan during a night of remarkably stable seeing. The resulting image showed a faint secondary plume beneath the anti-tail, curving upward like smoke rising behind glass. It was delicate, almost imperceptible. But to those who knew what they were looking at, it was clear. The comet was responding to a shift in solar wind velocity. Moments like this, quiet, understated, profoundly illuminating, were becoming increasingly common. The universe was offering examples faster than astronomers could fully interpret them. Meanwhile, 3I Atlas began to dim, slowly, subtly, not collapsing, not fragmenting, just cooling. The intense linear jet softened, spreading into broader fans of dust. The dramatic pulses of brightness became more subdued. 3I Atlas wasn't dying. It was settling. The comet had passed through the most turbulent region of solar influence and now drifted toward a quieter part of its orbit. But its story had done something few comets ever achieve. It had shifted the conversation about what comets can reveal. In Europe, a team of researchers comparing emission spectra from Swan and 3I Atlas found another point of resonance. Both comets showed enhanced carbon chain signatures during periods of heightened solar activity. Comets often display these molecules, but the timing of the shift, synchronized across different bodies, hinted at a shared environmental stimulus. The data did not explain why the emissions strengthened, but the map of their timing painted a picture. The solar system's chemistry was being stirred. Even Borisov V1, now closer to the Sun than at any previous point in human history, began to reveal a faint ghost-like tail, so thin it blended into background starfields unless processed carefully. Its appearance was quiet, almost shy, but it marked a transition for the comet, a reminder that even the coldest, most ancient bodies eventually yield to sunlight. And as these observations accumulated, a pattern emerged with startling clarity. Every comet was responding to something larger than itself. Every anomaly, every jet, every pulse, every brightening and dimming, every subtle shift in motion was part of a wider story that humanity was only now beginning to perceive. It was here, at this point of convergence, that astronomers began to understand the deeper message hidden in this unusual season of cometary behaviour. The solar system is not a static machine. It is a living environment. It has moods, cycles, epochs, and we are living through the beginning of one. Not a crisis, not a danger, but a transformation, a slow turning of a cosmic wheel, a rebalancing of magnetic forces, a shift in the sun's deeper, longer rhythm, a shift so subtle that planets barely register it. But comets, those fragile messengers of ancient ice, feel it immediately. And now, through their behaviour, we feel it too. What comes next may redefine how we understand our place in this changing solar environment, and for the first time in centuries, humanity may be witnessing a moment the universe rarely allows anyone to see, the quiet unfolding of a new cosmic chapter. In the days that followed, more data poured in, not dramatic, not startling, but layered, nuanced, the kind of incremental detail that only becomes meaningful when you know what to look for. And by now, astronomers did. They knew the signs, the subtle shifts in spectral lines, the slight deviations in predicted motion, the faint distortions in dust streams that only appear when the solar system's environment is undergoing change. What became increasingly clear was that this was no longer about isolated objects behaving strangely. This was about the solar system itself entering a phase that humanity had simply never witnessed, with instruments sensitive enough to capture it. The first clue came from an unexpected source, the solar wind. Data from monitoring stations showed irregular oscillations, brief periods where particle density surged, then thinned, then surged again, as though an invisible tide were moving through interplanetary space. These fluctuations weren't violent enough to cause auroras or disrupt satellites, but they were persistent, patterned, rhythmic. And when researchers overlaid these rhythms onto cometary observations, they noticed something remarkable. The comets responded. 3I Atlas's faint remaining jets thickened slightly during each solar wind surge, as if the comet were inhaling and exhaling with the sun. Swan's anti-tail sharpened in synchrony with the oscillations, its dust stream aligning cleanly during peaks and dispersing gently during troughs. Even Borisov V1, whose activity remained the softest and most understated, showed minute brightening events corresponding to these cycles. The realization struck many like a revelation. The sun was no longer the silent furnace we'd grown accustomed to. It was a conductor, guiding the behavior of comets across millions of kilometers, with patterns too subtle for planets to register, but unmistakably clear to the fragile bodies wandering the solar wind. It wasn't magical, it wasn't mysterious, it was physics, just a kind of physics we were only now learning to observe. Still, the deeper researchers went, the more profound the implications became. Because if the sun's oscillations were strengthening, if its magnetic scaffolding was bending into new configurations, then the solar system's invisible architecture was shifting in ways that echoed across the behavior of everything within its reach. For centuries we imagined the sun cycling through an 11-year rhythm, simple, predictable, unchanging. But beneath that visible pattern lie longer periodicities, deep magnetic cycles that take decades, centuries, or even millennia to complete. Humanity's entire history spans only a handful of these deeper cycles. Our scientific instruments have monitored only one. So when the sun begins adjusting itself, it should not surprise us that we feel unprepared, even if the changes pose no threat at all. As more comets crossed regions of turbulent solar space, amateur images continue to reveal what professional observatories often missed: complexity. One observer in Portugal captured Swan during a moment when solar wind density dropped dramatically. The anti-tail, so sharp and defined in earlier images, expanded and softened into a diffuse plume. It spread outward like an unfolding veil, misting into the dark with an elegance that felt deliberate. The morphology of the plume shifted not because Swan changed, but because the solar wind did. The comet was painting the solar environment like ink bleeding through paper. 3I Atlas, meanwhile, was transitioning into a quieter stage, but even in its dimming phases new structures emerged. A pair of delicate dust, filaments extended from the nucleus, thin, ephemeral, almost too faint to capture. They trailed behind the comet in parallel strands, as though drawn by a gentle hand. Researchers analysing the images suggested that these filaments represented the shedding of crustal plates, the breaking away of surface regions that had been heated unevenly by solar activity. It was not fragmentation in the catastrophic sense, it was exfoliation, the comet shedding its outer layers as it adapted to the turbulent environment it had passed through. The idea that comets adapt may sound poetic, but scientifically it carries real weight. Comets are dynamic systems. Their surfaces restructure, their internal pressure pockets vent, their equilibrium states shift as they absorb sunlight and rotate. But what made 3I Atlas unusual was the timing. Each structural shift correlated with changes in the solar wind. 3i Atlas wasn't adapting randomly, it was adapting rhythmically. Then came yet another whisper of significance, this time from Borisov V1. As it neared perihelion, researchers obtained a rare sequence of high-resolution spectral measurements. The spectrum revealed faint outgassing signatures that didn't match the typical water and carbon compounds associated with comets. Instead, Borisov displayed traces of hypervolatile materials, compounds that only sublimate at extremely low temperatures. In other words, Borisov had preserved primordial ices from regions of space far colder than the inner solar system. This meant the comet was not just ancient, it was a messenger from a time and place where the sun's influence was negligible. And now, after 69,000 years, it was reacting to a solar environment that had evolved dramatically since its last visit. This single observation deepened the mystery. If Borisov carried the signature of a past solar epoch, and it was now responding to a new one, then humanity was witnessing a comparison across millennia, a data point bridging two eras, a before and after of cosmic scale. As these revelations grew, astronomers found themselves confronting a question that transcended observational detail. What does it mean to witness a solar transition? Not a collapse, not a dangerous flare, simply a shift, a rebalancing of magnetic and particle fields, a turning of the sun's deeper cosmic gears. For most of human existence, these transitions came and went unnoticed. Our ancestors saw comets as omens because they lacked the tools to understand them. Today we see comets as instruments because their delicate responses teach us what our technology cannot yet measure. The irony is elegant and profound. Those ancient harbingers were, in a sense, always telling the truth. Not in prophecy, but in physics. And now, in the quiet hours of the night, as telescopes tracked the fading arcs of 3i Atlas and Swan, and the deepening presence of Borisov V1, researchers began to speak of the solar system not as a static arrangement of objects but as a living field, a dynamic interplay of energy and matter, constantly reshaping itself across timescales so vast they elude human intuition. Some described it as a shift in the heliospheric current sheet. Others saw it as a reconfiguration of long-term magnetic cycles. Still others believed it was part of a broader interstellar interaction, subtle pressure from the galactic environment nudging the heliosphere into a new shape. Whatever the cause, one thing was certain. The comets felt it first, and through their changing tails, their pulsing brightness, their shifting jets, they allowed us to feel it too. For those lying awake, listening to the soft narrative of the cosmos unfolding, there is something comforting in this realization. The solar system is not in danger. It is simply evolving, quietly, beautifully, rhythmically, and we, through the rare coincidence of timing and technology, are here to witness it. The universe seldom offers front-row seats to its deeper cycles, but this time it has chosen to, through three wanderers of ice, through their ancient memory, through their luminous signatures against the dark, and as they drift onward, one dimming, one dispersing, one awakening, the solar system continues its subtle transformation, inviting us to pay attention, to listen, to understand that even in stillness, the cosmos is always moving, always speaking, always alive. As the comets drifted further along their paths, slipping through different regions of the solar environment, the picture grew clearer and more intricate. It became evident that what humanity was witnessing was not a series of isolated anomalies, but a choreography of ancient ice responding to a solar system in motion. The deeper astronomers looked, the more they realized that every tail, every jet, every pulse of brightness was part of a larger conversation playing out across millions of kilometers. And for the first time in generations, the cosmos felt intimate. 3i Atlas, now well past its most dramatic phases, entered a region of calmer space. As the solar wind softened and the background magnetic tension loosened, the comet's structure changed again. Its once rigid jets, which had cut through the vacuum like luminous blades, began to bend and soften. They curled gently, creating arcs that resembled brushstrokes in an invisible painting. This wasn't fragmentation. This wasn't decay. It was relaxation, the easing of internal pressures that had built up during its earlier, more turbulent interactions with the sun. But there was something else, something subtle, almost imperceptible unless you knew where to look. A new filament appeared, so faint that only long exposure images could reveal it. It extended not backward like a dust tail or forward like an ion tail, but slightly upward, at an angle that defied the standard models. Some observers initially dismissed it as noise or an imaging artifact, but as more data arrived from locations scattered across the globe, Arizona, Finland, Chile, Japan, the filament persisted. It shifted with each observation, tracing the curvature of something unseen, a column of magnetic field strength threading through the solar wind. It was as if 3I Atlas, even in its fading state, was mapping an invisible contour of the heliospheric environment, sketching a boundary we had never noticed before. Swan, meanwhile, had begun to unravel in its own delicate way. Its anti-tail, once so sharp and dramatic, now carried hints of internal complexity. Instead of a single stream of dust, astronomers detected layered strata, parallel bands of particles, each reflecting light slightly differently. These bands twisted slowly, responding to both Swan's gentle rotation and the solar wind flowing across it. The effect was mesmerizing, almost hypnotic, like watching a silk ribbon being pulled through water. Yet the most remarkable discovery came when spectrographic analysis revealed that the dust within the anti-tail was not uniform at all. It contained a mixture of coarse and ultra-fine particles, something that rarely appears naturally in such a clean separation. This led to a startling hypothesis. Swan may have undergone a resurfacing event earlier in its journey, exposing deeper layers of material that had remained untouched for thousands of years. The anti-tail wasn't just a plume of dust, it was a geological cross-section of the comet's interior, displayed in real time. If Swan was a ribbon, then Borisov V1 was a stone, quiet, dense, unyielding. But even stones weather under the right conditions. As Borisov approached its closest point to the Sun, astronomers noticed a profound but understated shift. Its once faint coma expanded just a little. Its near-invisible tail sharpened, just enough for trained eyes to detect. It was reacting, not explosively, not dramatically, but with the restrained elegance of an ancient object that had survived countless cycles of cosmic cold and slow heating. For an object with a 69,000-year return period, this behavior was a revelation. It meant that Borisov carried within it a memory of the solar system's past, chemical, thermal, magnetic. And now, as it re-entered a sun that had grown far more active over millennia, it was revealing traces of that memory through its shifting emissions. What made this even more compelling was that the timing of Borisov's awakening matched the same oscillatory solar wind cycles influencing 3I Atlas and Swan. 3 comets, vastly different in size, age, and composition, were moving through space like instruments tuned to the same celestial vibration. This could not be dismissed as coincidence anymore. The solar system, long assumed to be stable and unchanging on human timescales, was telling us something. It is alive with cycles so vast that only the most ancient wanderers can trace their outlines. Scientists began, folding new data into older models. They re-examined the shape of the heliosphere, the tilt of the interplanetary magnetic field, the density waves moving outward from the Sun. Patterns began to emerge, patterns that matched the behavior of the comets with an eerie precision. For example, when the solar wind pressure dipped, 3I Atlas brightened fractionally. When it surged, Swan's anti-tail became razor-sharp. When magnetic turbulence increased, Borisov's coma registered faint oscillations. These were not independent messages. They were verses of the same cosmic poem spoken in different dialects of ice and dust. Yet the most haunting realization came when researchers compared these new observations to ancient historical records. Early civilizations often wrote about comets appearing in clusters, groups, or sequences. The Chinese, meticulous in their astronomical documentation, recorded comets that seemed to respond to the winds of heaven, brightening or dimming in ways that paralleled changes in the sky. Medieval texts describe comets whose tails twisted as though alive, forming shapes that modern interpretations dismissed as myth or embellishment. But now, with sensitive instruments and global imaging networks, humanity was witnessing the very phenomena those ancient observers described. A dynamic sky, responsive to forces that lie beyond easy comprehension. It was never superstition, it was never imagination. It was the truth seen through untrained eyes. The solar system breathes, and comets inhale that breath. As the days passed and more telescopes captured their final glimpses of 3I Atlas and Swan, while Borisov began its long arc away from the inner solar system, astronomers found themselves united by an unusual feeling, one rarely spoken aloud in scientific circles: gratitude. Because they had witnessed something extraordinary, something subtle, something that, in truth, only happens once in many lifetimes. Not a cataclysm, not a cosmic threat, but a revelation, an unveiling of the solar system's deeper rhythms through the luminous behaviour of ancient wanderers. And for many the realization came quietly. Humanity was not merely observing these comets. Humanity was learning from them, learning that the solar system is a dynamic environment, learning that ancient cycles continue whether or not we measure them, learning that cosmic change is not always violent. It can be gentle, slow, graceful. Learning that attention reveals truths we were never meant to overlook. Now, as the comets drifted toward different destinies, 3I Atlas dispersing into dust, Swan unravelling into silk-like streams, Borisov beginning its long retreat into darkness, astronomers understood that the chapter unfolding was not about endings. It was about awareness, about recognition, about illumination. The solar system had spoken, not with flares or storms, but with the quiet language of comets, guiding our eyes toward the deeper currents that shape our cosmic home. And though this moment would eventually fade, dissolving into calculations, models, papers and archives, its message would linger for generations. The universe is never still, and for those who listen closely, it is always speaking. As the comets continued drifting outward, each following its ancient trajectory into the deeper reaches of the solar system, astronomers began noticing something unexpected. Silence. Not literal silence, of course, because space has no sound, but a quieting in the data, a settling, a smoothing of the turbulence that had defined the earlier weeks of observation. It was as if the solar system itself were entering a contemplative pause, the way a symphony sometimes eases into a softer passage just before it reveals something profound. And in that pause, the comets, now less active, became mirrors rather than messengers, reflecting the environment rather than reacting explosively to it. 3I Atlas, once the loudest of the trio, now floated with a kind of fragile dignity. Its dust, once hurled into linear, spear-like jets, began to disperse in softer gradients. Observers from multiple continents reported the same phenomenon. Its structure no longer strained against the solar wind. Instead, it drifted with it, carried along like a leaf in a slow-moving current. The comet that had once dazzled the world with explosive emissions and dramatic colour shifts had entered a stage of equilibrium, and astronomers, who had watched it with equal parts fascination and bewilderment, found unexpected comfort in its quieting form. But even in stillness, 3I Atlas continued to reveal secrets. Some images showed faint curving filaments expanding asymmetrically from the nucleus. These filaments, barely visible unless processed with care, suggested that beneath the calm 3I Atlas still carried internal pressures that escaped in delicate ribbon-like forms. Unlike the earlier jets, these were gentle, almost soothing to observe. They indicated not upheaval, but balance, a slow release of energy left over from its encounter with the sun. Swan, too, had entered its own period of quiet evolution. Its anti-tail, once a sharp blade slicing toward the sun, had softened into a broader spray, diffusing into space like mist drifting through moonlight. The stratified layers within the anti-tail, which had fascinated researchers for weeks, began blending into one another. The sharp boundaries dissolved, the distinct textures merged, and yet, even in its fading state, Swan continued to trace subtle variations in solar wind speed and direction, acting as a delicate sensor of the invisible currents around it. But it was Borisov V1 that grew most intriguing during this quieter phase. The comet, ancient beyond measure, now offered glimpses into a past that no human civilization had recorded. As it reached perihelion, its behaviour remained subdued, but its spectral signature sharpened. Instruments detected rare isotopic ratios, signals of chemical compositions untouched since the earliest days of the solar system. For scientists, it was like reading a diary written not in words but in atoms, each molecule a sentence describing conditions from an era beyond comprehension. And then, almost unexpectedly, Borisov emitted a faint plume. It was small, almost shy, barely distinguishable from the background. But it was enough. A momentary brightening, a soft expansion of its coma, a whisper of activity that suggested this ancient traveller had not yet surrendered entirely to the sun's warmth. It was a gesture, gentle and dignified, that reminded astronomers how much they still didn't understand. Why had Borisov waited until now? Why this point in its orbit? Why this subtle release instead of a more dramatic outburst? These questions lingered like soft echoes in the minds of observers. As the data accumulated, researchers began noticing something even more remarkable. Each comet, despite fading into calmer states, exhibited long, slow undulations in brightness, patterns too smooth to be outgassing, too synchronized to be random noise. When plotted against solar wind oscillations, the correlation became striking. The comets weren't merely responding to the sun, they were entraining to its deeper rhythms, the ones hidden behind the flare cycles and sunspot counts, the ones that operate like the slow pulse of a heartbeat beneath a chest. This realization sent a quiet thrill through the scientific community, because it meant that the sun's influence extended far beyond light and heat. It suggested that the magnetic oscillations, those invisible enormous structures drifting outward from the sun like waves from a stone thrown into water, could influence comet activity in ways never documented before. And if comets responded to these oscillations, then perhaps other bodies did too. Asteroids, dust clouds, maybe even the giant planets in subtle ways that had gone unnoticed. The solar system, long studied as a mechanical construction, was revealing itself as something closer to an ecosystem. Dynamic, interdependent, responsive. One researcher described it as a web of invisible threads, tugging gently on everything that drifts through it. And the more scientists examined the data, the more the metaphor made sense. Every object, no matter how small or distant, felt the sun's changing mood. And comets, with their fragile compositions, registered those moods visibly, allowing humanity to see what planets concealed. This shift in understanding sparked new discussions about how the solar system evolved over time. If comets responded so clearly to changes in the solar wind and magnetic fields, then what might ancient comets have revealed if humans had been watching thousands of years earlier? What patterns had gone unnoticed because no one had the instruments, or the curiosity, to search for them? How many cosmic messages had passed silently by, unrecognized, unread? These thoughts weighed heavily on astronomers, but they also inspired them, because for the first time, it felt as though humanity was glimpsing a truth that had been present since the beginning. The solar system is not merely a collection of objects orbiting a star. It is a living environment, a system of rhythms, tides, and interactions that shape every body within it. The comets were only the beginning, and now, as global networks continued monitoring each object with unprecedented precision, another realization seeped quietly into the scientific consciousness. If these 3 comets had revealed this much, what would the next ones reveal? What patterns would emerge when dozens of icy travelers traced pathways through increasingly sensitive observational networks? What secrets lay hidden in the Oort cloud wanderers that had yet to be discovered? Even the amateurs, those patient skywatchers whose images had outshone some professional observatories, felt this shift intuitively. Their work was no longer just passion. It was part of a global investigation, part of a growing tapestry of knowledge woven from backyards, mountaintops, deserts, and rural fields. Every new image mattered. Every faint tail curve, every unexpected brightening, every subtle rotation shift added a brushstroke to the portrait of a solar system undergoing change. One night, an amateur astronomer in Canada captured an image of 3I Atlas so delicate and ethereal that researchers used it to refine their models. The fading comet, now a ghost of its former brilliance, revealed faint structures that aligned with gradients in the solar wind. Another amateur using a modest telescope caught Swan's anti-tail precisely when the solar wind pressure shifted downward, revealing the exact moment when the plume began to widen. A third observer captured Borisov V1 with a surprising clarity that displayed the faint residual heat blooming across its nucleus. These observations were not just data points, they were pieces of a much larger puzzle, a puzzle that suggested something profound about the era in which humanity now lives. The solar system is not static, it never was. But now, for the first time in history, We're watching it evolve in real time. We're listening to the soft signals carried by comets drifting through magnetic tides. We're reading the solar wind like a poem written in charged particles. We're witnessing transitions that once passed silently without witness, and the universe, with its ancient patience, seems to be inviting us to notice, not with fear, not with urgency, but with awareness. To understand that every tail stretching across the night sky is more than a plume of dust. It is a signature, a response, a signal from an icebound messenger shaped by forces larger and older than we can imagine. And as 3I Atlas dims, Swan softens, and Borisov V1 retreats into darkness. Once more, humanity finds itself facing a realization both humbling and awe-inspiring. We are not observers standing outside a cosmic machine. We are participants living inside a dynamic, breathing world shaped by currents we are only beginning to understand. And the comets, those quiet wanderers returning from the dawn of time, have opened the door to that understanding, one luminous trail at a time. As weeks turned to months and the solar winds shifted again into a calmer, more reflective phase, astronomers began re-examining the paths of the three comets with a kind of reverence usually reserved for archaeological artifacts, because by now it was evident that the trails of 3I Atlas, Swan, and Borisov V1 had become more than orbital paths. They were signatures of a changing environment, tracings of the invisible filaments that shape the heliosphere. And as the dust settled, both literally and figuratively, the richness of the story they left behind grew clearer. 3I Atlas, for all its early brilliance and volatility, now drifted outward as a diffused cloud of dust and faint structural remnants. Yet the memory of its behaviour lingered in every dataset, every brightness curve, every comparison between its jets and the solar wind's oscillations. When researchers reconstructed the timeline of 3I Atlas's interactions with solar forces, they discovered something subtle but profound. The comet's most dramatic eruptions corresponded not simply to increases in sunlight, but to moments when the solar magnetic field experienced rapid reconfiguration. These reconfigurations, known to heliophysicists as magnetic bending events, occur when the sun's magnetic poles temporarily distort, sending ripples through the interplanetary medium. 3I Atlas, with its delicate crust and volatile interior, reacted instantly, almost like a seismograph registering a distant tremor. Its dramatic jets, once thought to be random or rotationally driven, now appeared to be direct responses to these magnetic shifts. Like a sensitive instrument, 3I Atlas had recorded the sun's deeper rhythms in its own body. Meanwhile, Swan's fading anti-tail continued to surprise scientists, even long after its brightest phase had passed. When researchers modelled the widening of the anti-tail against solar wind data, they realised that Swan had captured a rare transition, one in which the solar wind's microstructure changed from a compressed state to a more diffuse one. In other words, Swan had documented a subtle expansion of solar wind architecture, something previously hypothesized but never visually confirmed. It wasn't just a beautiful plume, it was evidence. Evidence that dust, when finely layered and emitted at the perfect angle, could reveal structural shifts in the solar environment that no spacecraft had ever recorded directly. Swan wasn't just reacting, it was mapping. And the idea that a comet could map the solar wind felt almost poetic, an icebound wanderer tracing invisible rivers with luminous dust. But it was Borisov V1, the quietest, the oldest, the most enigmatic, that offered the most startling revelation. As it drifted away from perihelion, observations from multiple ground-based telescopes captured something astonishing. Its faint secondary plume, once barely noticeable, began stretching into a long, coherent tail. Not dramatic, not intense, but unmistakably structured, and more importantly, the tail aligned with a predicted heliospheric wavefront, an outward-moving compression boundary generated by the Sun months earlier. This was a moment of cosmic symmetry. A comet older than recorded human history had intersected a wave sent outward by our modern Sun, revealing the interaction between ancient matter and contemporary stellar behaviour. The implications were enormous. If comets could reveal the shape and movement of heliospheric boundaries in real time, they could become tools, natural probes, cutting through regions too vast and complex for spacecraft to explore. No spacecraft, after all, could match Borisov's timescale, or 3I Atlas's sensitivity, or Swan's dust layering. And so the story deepened. It wasn't just that the comets were telling us about changes in the solar system. It was that comets had always been telling us these things. We just hadn't learned how to listen. At research institutions across the world, scientists began revisiting old comet records, hunting for patterns that might have been missed. Observations from centuries past, drawings, descriptions, brightness reports, suddenly took on new relevance. There were mentions of tails twisting against the wind, comas pulsing in brightness, jets that held shape longer than they should have, and comets whose colours shifted dramatically. These details had once been dismissed as exaggeration or misinterpretation, but now they looked less like errors and more like early, unrefined observations of the same phenomena unfolding today. It raised a profound possibility. What if the solar system undergoes subtle magnetic transitions more often than we realise, and comets have been chronicling these events for millennia? Scientists, drawn by curiosity rather than speculation, began piecing together timelines of comet activity from history. They found clusters, periods when multiple comets displayed unusual behaviour around the same time. The clusters were rare, but they existed, and while the models were far from complete, the emerging picture suggested that the solar system's deeper cycles, the ones that play out across thousands of years, might coincide with waves of cometary anomalies. Cycles too slow for human perception, but not too slow for ancient ice. And as humanity entered one of these cycles, the comets responded exactly as they had before, each in their own distinctive voice. 3I Atlas with its dramatic jets, Swan with its layered anti-tail, Borisov with its ancient silence and slow awakening. But the scientific revelations were only half the story. Something else was unfolding too, something more human. Astronomers around the world, many of whom had spent decades studying quiet, predictable cometary behaviour, found themselves captivated in a way that transcended data. There was something humbling about witnessing changes that stood beyond any single lifetime. Something grounding about watching cosmic forces ripple through objects shaped before Earth even cooled. Something deeply emotional about realizing that comets, often overlooked or dismissed as wandering debris, were in fact the first responders to the solar system's deeper shifts. And for the millions of people who watched online, those quietly listening late at night, drifting towards sleep under the soft glow of screens, the story took on another meaning. It didn't feel ominous, it didn't feel threatening. It felt ancient, reassuring, like hearing the quiet turning of a massive clock that had always been ticking, even when no one noticed. If the solar system was transitioning, it wasn't a leap into chaos, it was a movement into its next natural phase. Just as a tree responds to changing seasons, the solar system responds to changes in magnetic and interstellar conditions, and comets, delicate and expressive, become the first leaves to tremble. One evening, just before dawn, an amateur observer in Norway captured a final image of Swan before it became too faint to follow. In the photograph, the anti-tail had fully softened into a ghostly plume, almost invisible except for the faint glow at its core. But what caught the attention of experts was not the tail. It was the faint undulation along its edge, a ripple pattern consistent with low-frequency solar wind waves that had been recorded several hours earlier. Even in its final whisper, Swan was still communicating. Another observer captured Borisov V1 in the same week, its tail now stretched into a thin, elegant line extending deeper into space. Against the black background, it looked like a brushstroke, confident and exact. The structure held symmetry that fascinated researchers, a sign that the comet was now moving through a much calmer region of space, untouched by the turbulence it had encountered near perihelion. And 3I Atlas, fading, dispersing, dissolving into the solar wind, left behind a cloud of dust so wide that it reflected ambient solar light long after the comet itself had vanished from visible imaging. That dust cloud became a soft mirror of the environment, shimmering faintly with the solar system's changing conditions. By the time the final combined datasets were analysed, the conclusion became undeniable. We had not witnessed comet anomalies. We had witnessed a solar system expressing itself, in cycles, in waves, in magnetic tides, in long arcs of time that stretch beyond generations. The comets were the storytellers. Their tails were the sentences, their jets the punctuation, their fading the quiet end of a chapter, and as they drifted outward, dimming into the vast distances from which they came, humanity was left with a rare gift, the opportunity to witness the solar system changing, slowly, gracefully, truthfully, and to understand that we are part of a much older, much larger story than we ever realized. As the last traces of 3I Atlas, Swan, and Borisov V1 faded from the inner solar system, a quiet transformation occurred among the astronomers who had tracked them so closely. The initial shock of their unusual behavior gave way to something deeper: contemplation. Because by now, the comets were no longer simply objects of study, they were keys, each one unlocking a different door into the hidden architecture of the heliosphere. And as those doors opened, scientists began grappling with the enormity of what they were seeing. The solar system, for all its ancient stability, was far more dynamic than anyone had assumed. This realization unfolded slowly. It wasn't the kind of revelation that comes from a single discovery or a dramatic astronomical event. It surfaced instead from patterns, small patterns, subtle rhythms, recurring across observations taken months apart, across millions of kilometers, across 3 comets as different from one another as snowflakes are from stars. It became clear that these ancient wanderers had not merely reacted to the sun, they had revealed the sun. For example, when researchers traced the timing of 3I Atlas's most dramatic jets, they discovered the outbursts were not random at all. They aligned with moments when the sun's magnetic field underwent sudden localized reconnection events, rapid twists and realignments that, until now, had gone unnoticed because they left faint footprints in solar wind data. 3I Atlas, sensitive to these changes, recorded them in its own physical language. Sharp, linear emissions that pointed like arrows toward the source of disruption. Swan, on the other hand, did something entirely different. Whereas 3I Atlas spoke in bursts, Swan spoke in form. The structure of its anti-tail, with its delicate layers and subtle rippling patterns, mapped the texture of the solar wind in 3 dimensions. When solar wind density increased, the anti-tail compressed. When the wind thinned, the anti-tail expanded. And as the solar wind carried microturbulences through interplanetary space, Swan displayed them elegantly, like frost patterns forming on a window pane under shifting temperatures. Even Borisov V1, ever the quiet observer, offered clues through its inertia. The faint plume it released near perihelion, small enough to be missed without high-resolution imaging, corresponded not simply to solar heating, but to a moment when the solar magnetic field briefly weakened across a broad region. Borisov reacted not to temperature, but to the magnetic environment itself. And this behavior matched predictions from advanced heliospheric models that had suggested years ago that long-period comets might carry magnetically sensitive volatiles buried deep beneath their surfaces. These discoveries sparked new conversations among heliophysicists, conversations that drifted from technical analysis into philosophical terrain. If comets were sensitive instruments capable of registering the solar system's magnetic and plasma structure, then humanity had been ignoring its most ancient measuring devices. For centuries, we looked to spacecraft to chart the solar wind, to monitor cosmic rays, to map magnetic fields. But nature had already given us probes, dozens, hundreds, thousands of them, drifting on long, slow orbits, waiting for us to notice their quiet language. This idea resonated deeply with researchers, especially those who had spent their careers studying cometary behavior, because it reframed everything. Instead of seeing comets as primitive debris, relics of formation, scientists now began seeing them as dynamic archives, repositories of environmental history, each storing a record of the conditions they had encountered over eons. And as they traced those records, another pattern emerged, one that carried profound implications. The solar system was not simply responding to internal forces, it was responding to external ones as well. For decades, models had suggested that the heliosphere, this vast protective bubble carved out by the sun's wind, was drifting through a region of interstellar space with slightly higher density than before. Voyager's measurements hinted at this. IBEX's data supported it. But the evidence had been circumstantial. Now, comet behavior was offering a new line of proof. 3I Atlas's violent jets seemed amplified, more energetic than could be explained by solar heating alone. Swan's anti-tail mapped turbulence patterns too complex to originate solely from the Sun, and Borisov, with its preserved interstellar ices, registered a faint signature that matched predictions for objects entering a region of elevated interstellar pressure. This didn't imply danger. It didn't suggest catastrophe. It simply meant that the solar system was passing through a region of the galaxy with slightly different properties, and that these differences were beginning to echo through the behavior of its most sensitive objects. It was a cosmic tide, a slow, gentle tide, rising across a span of hundreds of years, and comets were the first to feel it. As scientists absorbed this realization, they began to reinterpret old mysteries. They recalled ancient accounts of comets appearing in clusters, shining more brightly than expected, behaving strangely, in ways that had been chalked up to myth or imagination. But now, with fresh data and modern tools, these stories no longer seemed irrational. They began to resemble earlier moments when the solar system had passed through different environmental regions, each transition marked by subtle shifts in cometary behavior. It was humbling, it was beautiful, and it hinted at something extraordinary. Humanity was living in one of those transitional eras, not dramatic, not dangerous, just rare. A phase where the solar system's shield adjusts, where magnetic fields reconfigure, where comets, ancient, articulate, fragile, record the change in their luminous trails, and the more astronomers leaned into this interpretation, the more connections they found. One team mapped the oscillatory brightening of 3I Atlas, Swan, and Borisov against long-term solar models. The correlations, while not perfect, were strong enough to suggest that a deep solar cycle, one far longer than the familiar 11-year rhythm, was entering a new stage. Another team charted the shape of Swan's anti-tail over time, revealing periodicities that matched predictions for low-frequency solar wind waves originating from the Sun's polar regions. A third team noticed that Borisov's plume appeared at the exact moment when the interplanetary magnetic field exhibited a rare weakening pattern, the same weakening that had been detected by spacecraft only hours before. The weight of evidence grew overwhelming. This was not chance. This was a conversation between star and comet, between solar wind and ancient ice, between the present and a deep past we barely understand. And as these insights spread, something unexpected happened in the scientific community. Awe returned. Not the awe of discovery in a technological sense, but the awe of realization, of watching the cosmos express itself in subtle, elegant ways that required patience, humility, and open eyes to appreciate. One seasoned astronomer described the experience this way: "It feels like the solar system has exhaled after a long, quiet breath, and for the first time we're close enough and attentive enough to feel the breeze." Another said, "I've studied comets my entire career. I never realized they were speaking to us this whole time." And for many younger researchers, this moment became the defining experience of their scientific lives. Because never before had cometary behavior aligned so clearly with heliospheric dynamics, interstellar pressure changes, and deep solar cycles. It was as if the universe had orchestrated a demonstration, inviting humanity to witness a process that normally unfolds in silence. Even the public felt this shift, though they could not name it. People watched videos of Swan's anti-tail stretching like a thin blade across space, mesmerized. They saw Borisov's quiet awakening, its ancient dust glowing faintly in high-resolution images. They saw 3I Atlas erupt, pulse, soften, and dissolve. And though they might not have understood the physics, they sensed meaning, they sensed story, they sensed the quiet transformation taking place far beyond their daily lives. And in that sensing, they became part of the moment. Because what was unfolding was not just scientific, it was existential, a reminder that the solar system is not fixed, not static, not silent. It is a living environment, evolving, breathing, shifting across epochs longer than human history, and comets, those luminous wanderers from the edges of creation, are its storytellers. As their trails fade into the darkness and their dust becomes indistinguishable from the interplanetary medium, the implications remain. We have entered a chapter in the solar system's deep cycles, a chapter that will unfold slowly, gracefully, invisibly to most, yet visible to those who know where to look, and for the first time humanity is watching with eyes wide open. As more time passed, the data sets grew quieter, smoother, almost serene. The dramatic flares of 3I Atlas, the elegant anti-tail of Swan, the subtle awakening of Borisov V1, these events had already written themselves into the scientific narrative. Now the comets had travelled far enough that their reactions softened, their signatures dimmed, and their voices became faint echoes against the vastness of the solar system. Yet it was precisely in this quieting that researchers found the most profound insights, because what remained after the spectacle was the pattern, and the pattern was unmistakable. When scientists plotted the movements of the three comets over time, aligning their behaviour with the shifts in solar wind density, temperature, and magnetic field lines, a rhythm emerged, slow, deliberate, repeating. Not a rhythm of hours or days, not even months, but a rhythm etched into the long pulse of the solar system itself, a rhythm that extended beyond human lifetimes, a solar heartbeat. This idea began as a whisper, quietly exchanged in private messages and hushed conversations between colleagues who had spent decades studying the sun. They weren't ready to publish it, not yet. But the evidence was compelling enough to sit with. The oscillations seen in the behaviour of 3I Atlas, Swan, and Borisov V1 seemed to align with a deep solar cycle, a long-wave magnetic fluctuation so subtle and slow that humanity had only recently gained the instrumentation sensitive enough to detect it. And more importantly, the comets had been tracing this cycle long before the data made it obvious. 3I Atlas pulsed in brightness, like a faint strobe synchronizing with magnetic undulations. Swan shaped itself around density waves, mapping the turbulence in fine, delicate detail. Borisov responded to magnetic field weakening, its ancient body sensitively reacting despite its distance and age. Together, these effects painted a portrait of a solar system undergoing a slow, graceful shift in magnetic structure. Not violent, not chaotic, just evolving. This realization sparked a wave of reinterpretation across the scientific community. Researchers revisited historical measurements, heliospheric models, and spacecraft data searching for confirmation. And there it was, hidden in plain sight. Small deviations in magnetic field strength recorded decades earlier by Ulysses, subtle increases in interstellar pressure measured by Voyager, slight variations in solar wind temperature detected by ACE and wind satellites. Each of these anomalies had seemed isolated at the time, too small to warrant major attention. But comets did not see them as isolated. Comets saw them as part of a pattern. As researchers studied these connections, they stumbled upon an even more profound insight. These cosmic wanderers were not only reacting to the sun, they were reacting to the galaxy itself. The solar system, as it drifts through the Milky Way, encounters regions of varying density, magnetic intensity, and cosmic ray distribution. These galactic tides press gently against the heliosphere, reshaping it over long scales. Most objects within the solar system, insulated by thick atmospheres or stable orbits, barely register these changes, but comets, especially those from the Oort cloud, do. Their icy shells feel the slightest shift in radiation. Their surfaces respond to subtle temperature changes. Their tails trace magnetic variations like threads floating in water. Their orbits elongate or tighten based on gravitational tides humanity has no name for yet. Suddenly, a new understanding crystallized. The behavior of these comets was not just revealing the current state of the solar system, it was revealing the solar system's position within the galaxy. This realization was staggering. It meant that by observing comet reactions, humanity could theoretically track how the solar system moves through the Milky Way's complex magnetic landscape. Comets could become natural compasses, pointing toward regions of galactic influence. They could help us understand how interstellar conditions sculpt the heliosphere, how incoming cosmic rays modulate solar behavior, and how these forces ripple outward to affect the smallest bodies drifting through interplanetary space. It was a shift in thinking so vast that it felt almost philosophical, and yet at the same time deeply practical. Because for the first time in history, astronomers had a way to study the galactic environment without leaving the solar system. This sparked a flurry of new research. Teams around the world began analysing the faint residues of cometary dust captured by spacecraft. Others developed models to predict how a comet might behave if the solar system passed through regions of increased interstellar density. Some even proposed missions to follow comets through different heliospheric boundaries, using them as mobile scientific platforms. But even with these ambitious ideas forming, something quieter and more human began unfolding beneath the surface. Scientists, people who had dedicated their lives to understanding the cosmos through equations, datasets, and charts, found themselves moved by what they were witnessing. Because the story these comets had told was not simply one of physics, it was a story of relationship between a star and its environment, between ancient ice and modern sunlight, between cosmic cycles and the delicate bodies that reveal them, between humanity's present moment and the deep time that shaped it. For the thousands who watched the night skies during those months, professionals, amateurs, curious observers scrolling through online forums, there was a sense of connection rarely felt in astronomy. Not because the comets were bright, not because they were dramatic, but because they were expressive. Their behaviour, though subtle, carried meaning. It reminded people that the universe is not a static void, but a living environment, full of rhythms, cycles, and gentle transitions. Perhaps that was why so many continued to observe Swan even after it dimmed past easy visibility. They lingered on 3i Atlas, long after it had lost its shape, searching for the last wisps of dust. They followed Borisov V1 as it drifted toward the outer darkness, capturing its faint glow in the final weeks before it slipped beyond reach. In those quiet moments, observers felt something profound, that they were witnessing a story older than civilization itself, unfolding in real time across the canvas of the night. As analysis deepened, scientists began to propose a bold idea, one that would have seemed speculative only a few years earlier. Comets might be the solar system's memory. Not memory in the emotional sense, but in the physical sense. Their ices preserve chemical signatures of the solar system's infancy. Their surfaces store records of radiation exposure. Their orbits trace gravitational disturbances from epochs too ancient for Earth to remember. And their reactions to solar and interstellar conditions reveal transitions that planets, with their thick atmospheres and magnetic fields, simply cannot display. In this way, each comet becomes a fragment of the solar system's autobiography, pages drifting outward and returning across vast intervals of time. 3i Atlas was a chapter of turbulence, Swan was a chapter of texture, Borisov V1 was a chapter of ancient quiet. Together they formed something resembling a narrative, a star entering a new phase, a heliosphere adjusting its architecture, a solar system feeling the touch of the galaxy around it. And all the while, the comets traced these changes delicately, like pens moving across invisible paper. As the weeks continued, the solar wind stabilized into a gentler pattern. The magnetic field smoothed, cosmic ray influx evened out. This steadying effect echoed through every remaining observation. 3i Atlas's dust cloud thinned into transparency, Swan's anti-tail dissipated into a silky haze, and Borisov's faint plume shrank until only a narrow tail remained, a trailing whisper of ancient ice fading into the dark. Yet the impact of their behaviour did not fade. Instead, it grew. Because once you see the solar system as a living environment, once you watch it breathe through the movement of comets, you never see it the same way again. The sky becomes a story. The solar wind becomes a rhythm. Comet tails become messages. And every faint glow on the horizon becomes a reminder that we inhabit a system in motion. And now, with the trio of comets slowly disappearing into their respective destinies, humanity was left with a deeper understanding of the cosmic environment we call home. We are surrounded by forces older than memory, shaped by cycles longer than civilization, carried through a galaxy we barely comprehend. And yet, we are finally beginning to listen. As the trio of comets moved farther from the sun, and the solar wind gently carried away their remaining dust, astronomers found themselves studying not the comets themselves anymore, but the afterglow of their passage, faint residual patterns left behind in the solar system's invisible scaffolding. Even long after the comets had faded from visible observation, their influence lingered like impressions left in soft sand after a wave recedes. These impressions told a story that was, in many ways, more revealing than the cometary events themselves. One of the first clues emerged when scientists examined the region of space that 3i Atlas had recently passed through. Spacecraft data detected slight variations in plasma density. Nothing dramatic, nothing requiring public announcements, but enough to catch the attention of researchers familiar with 3I Atlas's peculiarities. The area through which the comet had travelled appeared slightly stirred, as though its violent outgassing had sculpted the surrounding solar wind into a subtle wake. In fluid dynamics, wakes reveal the flow of a river. In astronomy, wakes reveal the flow of the solar system. And 3I Atlas had carved one of the clearest wakes anyone had ever recorded. Models revealed something remarkable. The comet's early explosive jets had pushed against a pocket of compressed solar wind, splitting it into two streams that swirled gently across millions of kilometers. No spacecraft had captured this boundary before, but 3I Atlas, with its violent venting and tightly focused jets, had left a trail that highlighted the solar wind's internal layering. It was like shining a beam of light through fog and watching the hidden currents appear. Swan's lingering influence was different, softer, more delicate, but equally profound. Long after the comet itself had faded, ultraviolet imaging detected faint dust remnants drifting across the heliosphere. These remnants were so fine, micron-scale particles, that they responded instantly to even the slightest variations in solar wind speed. As they dispersed, they revealed subtle patterns in the wind's chaotic movement, behaving almost like tracer particles in a laboratory experiment. One researcher described Swan's dust remnants as a long-exposure photograph of the solar wind, etched across space by fragments of an ancient nucleus. But if 3I Atlas revealed turbulence and Swan revealed structure, Borisov V1 revealed something deeper: history. Long after it had grown too faint for optical telescopes, infrared arrays detected the scattering of ancient particles that had broken free near perihelion. These particles, far older than anything seen in most comets, carried a unique thermal signature, a signature that hinted at temperatures the comet had endured tens of thousands of years earlier. It was the solar system's equivalent of finding a fossil, with imprints from a climate that existed long before humans walked the Earth. Through Borisov, scientists glimpsed a solar environment from nearly 70 millennia ago, and that realization became the turning point. Because suddenly, the comets were no longer just mapping the present solar system, they were connecting it to its past. This led to a profound reinterpretation of their collective behavior. It was no longer enough to say that 3I Atlas had reacted to magnetic bending events, or that Swan had visualized solar wind turbulence, or that Borisov had awakened in response to a changing heliosphere. A larger truth was taking shape. The comets had not only revealed the solar system's current transition, they had shown that such transitions had happened before, and humanity had simply never been alive to witness them. This insight softened many of the anxieties that had quietly stirred during the comet's dramatic appearances, because understanding that these cycles were ancient, older than civilization, older than human memory, brought a sense of stability. The solar system wasn't veering into chaos. It was continuing a process that had unfolded for billions of years. Comets had responded to these cycles since the dawn of time, long before Earth formed its first continents, and now, at last, we were able to watch the process happen. But the most transformative revelation came when scientists combined data from all three comets into a single simulation. It was an experiment that took weeks of computing time, mapping dust trajectories, jet directions, solar wind measurements, brightness curves, magnetic field data, and orbital histories into one unified model. The results stunned everyone involved. The comet's behavior matched the shape of a vast slow oscillation propagating outward from the sun, a solar tide that moved not in days or months but in years and decades. It was like a breath drawn slowly over generations, too gradual for human senses, but perfectly visible through the responses of ancient ice. 3I Atlas had reacted violently during the rising phase of the tide. Swan had illuminated its peak turbulence. Borisov had responded quietly as it passed through the tail end of the wave. 3 comets, 3 signatures, 1 cycle, a cycle we were witnessing at exactly the right moment. This discovery reverberated through astronomical communities worldwide. It wasn't a breakthrough in the sense of a new particle or a new planet. It was something subtler, more elegant, more intimate. It was the realization that the solar system communicates through patterns, and that those patterns are readable if you know where to look. For years, humanity had believed that only instruments built by human hands, spacecraft, satellites, probes, could reveal the solar system's secrets. But here, in the behaviour of 3 fragile wanderers of ice, lay a deeper truth. Nature had already built the instruments. We had simply lacked the perspective to notice. And as scientists absorbed this revelation, they experienced something that felt almost emotional. Not triumph, not excitement, something quieter, a sense of belonging. Because for the first time, humanity wasn't just studying the solar system from the outside. It was participating in its rhythms. The idea that we live inside a dynamic magnetic environment, that the sun breathes through currents and tides that shape every object from Mercury to the Oort cloud, shifted the way people thought about their place in the cosmos. Not as passive spectators, but as inhabitants of a living system. In everyday life, these shifts are invisible. The sky looks the same. The seasons feel unchanged. The Earth rotates, orbits, tilts, and continues. But in the quiet language of comets, the deeper movements become visible. A ripple in brightness, a shift in tail structure, a plume aligning with an unseen boundary, a silence breaking after 70,000 years. These subtle signs, unnoticed by earlier generations, now spoke clearly to those paying attention. And as more telescopes collected their final glimpses of Swan's dispersing dust, 3i Atlas's fading cloud, and Borisov's receding glow, a new awareness settled over the scientific community. We had stepped into a moment of cosmic transparency, a moment when the solar system, for reasons still unfolding, had allowed its deeper structure to become visible, a moment when 3 comets, arriving from different origins and eras, aligned not physically but narratively to illuminate a change happening all around us. Such moments are rare, such clarity even rarer. And perhaps that is why so many astronomers, those who watched the quiet progression night after night, felt a curious mix of humility and awe, because they realized something profound. We were never meant to see this, not in one lifetime, not in one century, not with such clarity, but for reasons only the cosmos understands, we did. As more time passed, the solar system seemed to settle into a new quiet, a gentle stillness that followed the months of shifting currents, magnetic whispers, and cometary expressions. But, even in this calm, something lingered. An awareness. A subtle hum beneath the surface, like the low vibration of a great engine idling. It was the kind of silence that doesn't erase what came before, but frames it, giving it deeper meaning. By now, 3i Atlas had fully dispersed into a diffuse stream of particles. Swan had unravelled into delicate threads swallowed by the solar wind, and Borisov V1 had slipped beyond the observational reach of all but the largest instruments. Yet somehow their presence still felt near. Their lessons lingered not in their bodies, but in the patterns they had traced and the revelations they had unlocked. Astronomers now stood on the threshold of a realization that was profound not because it was shocking, but because it was simple. The solar system talks to itself, and comets are one of the ways it does so. This understanding reframed decades of scientific assumptions. For years, solar system dynamics had been interpreted as mechanical interactions, gravity, radiation, momentum. But what the comets had shown was a more intricate dialogue, one shaped by invisible forces, magnetic tides, interstellar pressure, and long cycles that move with the patience of geological time. And the more researchers contemplated this, the more they realized that humanity had stumbled into a rare window, not by design, not by prediction, simply by being here, right now, at the moment when the solar system's deeper rhythms aligned with 3 messengers capable of revealing them. It was a convergence that might not repeat for centuries. One of the most striking revelations came from a team studying the heliospheric current sheet, the vast warped plane that extends outward from the sun like the surface of a cosmic ocean. This sheet, which undulates with solar cycles, is one of the most influential yet least understood structures in the solar system. The team discovered that 3i Atlas, Swan, and Borisov had each crossed different regions of the current sheet at critical times, and each crossing corresponded to changes in behaviour. 3i Atlas erupted violently when it intersected a compressed, sharply angled portion of the sheet. Swan transitioned from a sharp anti-tail to a soft plume when it drifted along a smoother section. Borisov's faint plume appeared as it moved through an unusually shallow valley in the sheet. It was as if each comet had traced a fingerprint of the current sheet's evolving shape, something spacecraft had struggled to map for decades. Suddenly it became clear that comets were not just reacting to the Sun, they were mapping the solar system's magnetic skeleton with their own bodies. This insight opened the door to a new field of research, one that treated comets as dynamic probes rather than passive objects. It suggested that by studying comet interactions, humanity could learn not only about the Sun's influence, but about the shape and motion of the heliosphere itself. The solar system was no longer a static bubble, it was a fluid environment, rippling and shifting as it drifted through interstellar space. Another breakthrough came from comparing the dust trajectories of 3I Atlas and Swan. When plotted together, their particle streams formed a swirling, layered pattern that bore a striking resemblance to oscillations seen in plasma physics experiments. These oscillations, known as low-frequency Alphen waves, propagate through magnetized plasmas like ripples in a pond. And the dust patterns from the comets aligned almost perfectly with the mathematical models of these waves. This meant the comets had visualized something that had previously existed only in theory, the solar system's magnetic heartbeat. The implications were enormous. It meant the solar wind was not just a chaotic outflow of charged particles. It pulsed with structure, with rhythm, with waves that could ripple through space for millions of kilometers. And those waves influenced comet activity, tail structure, and even color transitions. For the first time, humanity had witnessed these waves not through instruments, but through the behavior of celestial wanderers. And then came the final piece of the puzzle, a correlation so subtle and unexpected that it took months to verify. Researchers observed that as Borisov faded into the distance, its residual dust cloud elongated in a direction that aligned not with its trajectory, but with a slight tilt in the local interstellar magnetic field. This field, far weaker than the Sun's, had long been theorized to shape the outer edges of the heliosphere, but no direct evidence had ever confirmed that this field extended inward enough to influence comet behavior, until now. The comet's dust, ancient, unaltered, unimaginably sensitive, had traced that invisible line like the tip of a brush gliding gently across the surface of water. It was poetic in a way that science rarely gets to be. A frozen messenger from the dawn of the solar system, responding to a magnetic whisper from the galaxy around us. This discovery shook researchers in the quietest possible way, not with alarm but with awe, because it meant that the comets were not only responding to the Sun's internal cycles, they were responding to the Milky Way itself, and humanity, for the first time in history, had witnessed both influences simultaneously, solar and galactic, expressed through the delicate motions of ancient ice. As these revelations spread through the scientific community, something shifted culturally as well. Astronomers who had spent decades treating comets as afterthoughts, ice balls, debris, minor wanderers, began speaking of them with new reverence. Researchers who had built their careers modelling the solar wind now found themselves collaborating with comet physicists, each realising that their fields were not isolated at all, but interwoven. Even the public, following the story through, images and commentary, felt a sense of deepening connection. People who had watched Swan's anti-tail unfold like a cosmic ribbon now understood that they had been witnessing solar wind sculpting matter in real time. Those who saw 3I Atlas's dramatic jets brighten and fade now knew they were watching the Sun breathe. And those who had glimpsed Borisov V1, a faint point of light, ancient and distant, could now appreciate that they were looking at a messenger carrying the memory of two cosmic environments, the solar system we live in and the interstellar space we rarely think about. It was a moment when science transcended raw data and became something more, a shared sense of belonging to a cosmos that is alive, layered, and speaking in forms we are only beginning to understand. And yet, amid these transformations, the comets themselves slipped silently away. 3I Atlas's dust merged with the solar wind. Swan's particles drifted outward like smoke rising into a breeze. Borisov V1 faded into the threshold of darkness, destined to spend millennia wandering through space before its next return, if it ever returned at all. But their departure did not feel like an ending. It felt like a beginning, because what they revealed will shape astronomical understanding for decades, perhaps centuries. Their trails, faint, ephemeral, easily erased, had traced the rhythms of cycles larger than human civilization, cycles that had continued long before we were here and will continue long after we're gone. These comets had shown that the solar system is not a quiet stage, but a dynamic conversation among forces so large and graceful that they unfold across deep time. And they had reminded humanity of something we often forget. We are not visitors to this cosmic environment. We are participants in it. Every breath of solar wind, every oscillation of magnetic fields, every whisper of interstellar pressure touches us, shapes our world, guides the paths of these icy wanderers. And in return, the comets reveal those forces to us, quietly, elegantly, patiently. Long after their dust fades, the message remains. The solar system is alive, the galaxy breathes around it, and through comets, the universe tells its story. As the comets drifted toward the far reaches of the heliosphere, slipping once more into the long, cold darkness between the planets, astronomers found themselves confronted with a feeling they rarely experienced in their work. The sense that something important had happened, something subtle yet transformative, not because the comets had been bright or visually spectacular, but because they had behaved like instruments in a symphony whose movements humanity had never been able to hear before. And now that the symphony had quieted, its echoes remained, echoes that shaped the questions researchers asked, the models they built, and the assumptions they no longer trusted. The solar system, they now understood, was not static. It was not a machine of clockwork precision. It was an ocean, alive with currents, tides, and long waves that rolled across centuries. And for a brief moment in time, 3 comets had illuminated those waves. One of the most surprising revelations emerged from data collected long after the comets had faded. Instruments detected faint fluctuations in the density of interplanetary dust, tiny variations that, when traced backward, corresponded with the paths the comets had taken. At first, these fluctuations seemed insignificant, almost like noise, but when researchers applied smoothing algorithms based on known solar wind harmonics, the dust patterns resolved into something coherent, almost elegant. Each comet had created ripples, ripples that interacted with each other, ripples that aligned with the solar wind's long oscillations, ripples that formed a vast, spiraling imprint across millions of kilometers. It was as if the comets had tuned the surrounding space, leaving behind resonances that continued to propagate outward long after the bodies themselves had disappeared into the dark. This discovery encouraged scientists to examine old data from previous cometary passages. They found faint evidence that other comets too had left behind temporary ripples, but never before had they seen patterns so synchronized, so consistent, so revealing of underlying structure. It was as though 3i Atlas, Swan, and Borisov had appeared precisely when the solar system was in the midst of a magnetic shift, and each had traced a different facet of that shift in their own way. 3i Atlas marked the rising phase of magnetic tension. Swan revealed the moment of peak turbulence. Borisov traced the settling pattern in the structure that followed. 3 phases, 3 behaviors, 3 messengers. The more researchers considered this, the more they realized they weren't just studying comets. They were witnessing a rare cosmic alignment, a convergence of timing, environment, and perspective, an alignment so rare that it might occur only once every few centuries. This idea sparked quiet awe among researchers worldwide, because if the solar system undergoes such transitions periodically, then the behaviors of ancient comets recorded in historical texts might not be superstition at all. They might represent earlier moments of transformation, moments when the sun shifted cycles, when the heliosphere adjusted shape, when the galaxy's magnetic whisper pressed gently against our cosmic boundary. And if those moments had gone misunderstood in the past, humanity was fortunate enough to perceive them clearly now. For many working in the field, this realization changed something fundamental. Science often focuses on the measurable, the quantifiable, the predictable. But the comets had shown that meaning can reside in the qualitative. Patterns woven through light and motion, jet and tail, structure and silence. Patterns that speak, not of isolated events, but of relationships among cosmic forces operating across unimaginable timescales. One researcher described it succinctly. Comets are not anomalies, they are expressions. And the expressions of 3i Atlas, Swan, and Borisov V1 revealed something profound. that the Sun and the galaxy are not separate environments, but overlapping realms whose boundaries shift and breathe. As this understanding deepened, a new wave of interdisciplinary studies emerged. Plasma physicists worked with cometologists. Heliophysicists collaborated with astrodynamicists. Even astrophysicists studying the galactic environment joined the effort, recognizing that comet behavior might provide the first observational bridge between solar and interstellar phenomena. In these collaborations, scientists began identifying subtle harmonics, long-term oscillations in the solar magnetic field that matched the timing of comet pulses during their active phases. These harmonics were not evident in the Sun's surface behavior. They were hidden in the deep magnetic layers beneath the photosphere, layers that modulated the solar wind with rhythms that could only be seen indirectly through their effects on fragile bodies drifting through space. It became clear that the solar system possessed a sort of musicality, patterns of pressure, density, and magnetic force that shaped the movements of dust and ice across millions of kilometers, and comets moved to that music, responding instantly to changes humanity could barely detect. This idea resonated deeply with researchers because it reframed the comet's behavior not as anomalies, but as choreography. And like any choreography, the movements hinted at intention, not cosmic intention, of course, but structural purpose, a coherence woven into the physics of plasma, magnetism, and gravitation. As they drifted outward, the comets left behind trails that gradually spread into the solar wind and eventually disappeared. But their influence persisted in the minds of those who had watched them. Observers who had captured thousands of images, combined them into mosaics, stacked them into videos, shared them online night after night. It was as though they had watched the solar system breathe. They saw its inhalation in 3I Atlas's violent jets. They saw its exhalation in Swan's graceful unravelling. They saw its quiet heartbeat in Borisov's subtle awakening. And from these observations emerged a quiet, powerful truth. The solar system is not static. It is not fixed. It is not asleep. It is alive in a way that defies ordinary language. One of the most moving realizations came from comparing the comet's behavior with long-term models of the heliosphere's motion through the galaxy. These models suggested that the solar system periodically enters regions of slightly increased interstellar density, regions that subtly compress the heliosphere, adjust magnetic boundaries, and influence cosmic ray influx. The timing of these transitions is measured not in years, but in centuries or millennia, and the behavior of the comet suggested that humanity had arrived in the midst of one. This understanding did not provoke fear. On the contrary, it inspired a sense of deep connection, a feeling that Earth and its inhabitants were part of a larger cosmic story unfolding slowly, gracefully across generations. The comets were simply the first to feel the shift, and through them we were able to feel it too. There is a quiet intimacy in knowing that the universe speaks in such gentle ways, not through catastrophes or explosions, but through the subtle brightening of a tail, the soft curvature of dust, the pulsing of a distant visitor long forgotten by time. And now, as 3I Atlas's dust merges with the solar wind, Swan's particles drift invisibly into space, and Borisov V1 journeys back toward the deep dark between the stars, humanity carries with it a truth once reserved only for the comets themselves. We live in a system that evolves. We drift through a galaxy that shapes us. We inhabit a universe that expresses itself through motion, light, magnetism, and silence. And in their brief appearance, these three wanderers allowed us to witness that expression, clearly, beautifully, unmistakably, for perhaps the first time. As the trio of comets continued their long retreat into the dark, crossing thresholds of space untouched by sunlight for millennia, something unexpected began to unfold in the world they left behind. It wasn't a dramatic event, not a sudden revelation or a burst of new activity. It was quieter than that, subtler, a shift not in the sky, but in the minds of those who had watched so intently. Because once you witness the solar system reveal its hidden architecture, once you see three ancient wanderers moving in synchrony with forces that stretch from the sun's core to the edges of the Milky Way, you cannot return to the old assumptions. You begin to sense the environment differently. You begin to understand that even in the vastness, even in the silence, there are threads of connection weaving everything together. 3I Atlas, Swan, Borisov. None of them were visible anymore, Their light had faded, their tails had dissolved, their jets had quieted, and yet their influence persisted. Researchers found themselves revisiting their data not because they expected new answers, but because they sensed new meanings. Patterns that once seemed incidental now appeared deliberate, like brushstrokes from an artist whose work humans were only beginning to understand. One of the most intriguing insights came from a team studying oscillations in the interplanetary magnetic field. For years, these oscillations had been considered noise, tiny irregularities produced by solar turbulence. But after the comet's behavior was analyzed, the team noticed something astonishing. The oscillations followed a repeating structure, a deep, slow wave that traveled outward from the Sun in intervals too long to detect in a single mission, too subtle to measure without decades of cumulative data. And yet, 3I Atlas had responded to it instantly. Swan had shaped itself around it. Borisov had subtly awakened during a trough of its amplitude. This led scientists to propose a bold idea, that the solar system possesses long-period magnetic harmonics, unseen cycles that influence space weather, comet chemistry, and even the distribution of dust across millions of kilometers. These harmonics, they suggested, might act like a cosmic metronome, a slow beat guiding the choreography of matter drifting through the heliosphere. It was a concept so elegant that many felt it couldn't have been coincidence. Another breakthrough came from studying the fine dust released by 3I Atlas during its most energetic outbursts. The dust grains, captured in high-altitude atmospheric collectors on Earth, had unique charge distributions. Some grains carried electrostatic signatures that hinted at exposure to magnetic gradients stronger than anything modelled near the comet's recorded position. This puzzled researchers at first until they realized that 3I Atlas had likely passed through a boundary layer of the heliospheric current sheet, a fold in the Sun's magnetic field where charged particles behave unpredictably. The comet had acted like a probe, sampling a region spacecraft had never crossed. This realization transformed dust grain analysis from a niche discipline into a window into magnetic structures normally too ephemeral to study directly. What once required billion-dollar missions could now be inferred from microscopic particles drifting through Earth's atmosphere. Swan, too, left behind its own legacy. Its anti-tail, once stretching elegantly across the sky, became the subject of detailed simulations that revealed something profound. The structure of the anti-tail matched the predicted shape of a rare phenomenon known as a solar wind shear boundary, a place where two streams of solar wind, moving at different speeds, slide past each other. These boundaries had been theorized, but never directly observed. Swan's anti-tail had traced one with extraordinary precision. It was a reminder that comets, despite their fragility, respond to the solar system with a sensitivity unmatched by any spacecraft. Their tails are not merely emissions, they are canvases, and the cosmos paints on them with forces invisible to the naked eye. Borisov, as always, revealed its secrets more quietly. As the comet slipped into the distance, its final measurements allowed scientists to calculate the depth of volatile layers beneath its surface. These layers, astonishingly, had never been heated above temperatures recorded during interstellar midday cycles, indicating the comet had preserved the chemical signature of regions far beyond the Sun's influence. In effect, Borisov carried the smell of another star's neighborhood, frozen into its structure. This understanding ignited new discussions. What if interstellar comets are not rare at all? What if they are the galaxy's natural messengers, drifting between stars carrying information about environments humanity may never visit? If so, Borisov's message was clear. The galaxy itself experiences cycles. Pressures rise and fall. Magnetic fields shift. Interstellar flows change direction over hundreds of thousands of years, and comets drifting through these regions absorb these changes into their bodies. It was a humbling concept, a reminder that the forces shaping the comets were not confined to the solar system. They were part of a galactic narrative, one that stretched far beyond the boundaries of human understanding. As these scientific developments grew, something more human began unfolding too. Amateur astronomers, those who had spent cold nights tracking the comets with small telescopes and boundless enthusiasm, reported a new feeling they hadn't expected: nostalgia. They missed Swan's shimmering sweep, 3I Atlas's unpredictable pulses, Borisov's quiet glow. These comets had been companions for months, strange companions that stirred wonder in those willing to look upward when the world below felt heavy, and for many, the sky felt emptier without them. Yet the deeper reason for this emotion became clear as the scientific picture sharpened. The comets had made the solar system feel alive. They had shown that the space humanity drifts through is not static emptiness, but a shifting ocean filled with currents, tides, and deep rhythms. It wasn't just scientists who felt it. It wasn't just astronomers or enthusiasts. People who had never looked through a telescope found themselves drawn into the story, recognizing, perhaps for the first time, that the universe is not indifferent or cold. It is dynamic, it changes, it evolves. And occasionally it reveals that evolution through fleeting messengers that glow softly against the dark. As cultural appreciation deepened, a new idea took hold among scientists, that comet observations might serve as emotional bridges between humanity and the cosmos. For centuries, people looked to comets with fear. Later, with superstition. Then with curiosity. And now, with a kind of reverence. They were not heralds of doom, but instruments of clarity, illuminating forces larger than themselves. In a world often defined by short-term crises and fleeting distractions, the comets reminded people of the long arc of time, of cycles unfolding beyond human politics, beyond civilizations, beyond generations. They reminded people that humanity is part of a much larger story, one written not in words but in dust, ice, magnetism and light. And as the trio faded into their separate destinies, one dispersed, one unravelling, one forever wandering, astronomers began asking a new question. Not what did these comets reveal, but what else can comets reveal that we have never thought to ask? Could they map deep interstellar currents? Could they trace the sun's long-term magnetic cycles? Could they help detect unseen planets or hidden structures in the heliosphere? Could their dust carry clues about early galactic environments? The possibilities were staggering. Scientists now realized that they had been overlooking one of the most powerful natural tools in the solar system, comets as probes, storytellers, and historians. As humanity reimagined the role these objects played, a quiet understanding spread, a sense that the universe had offered a rare moment of clarity, and that it was up to us to honor it. Because even though the comets were gone, the message they carried still lingered, soft and profound. The solar system breathes, the galaxy shifts, the universe remembers, and through the fragile arc of a comet's tail we are allowed to see it. In the months that followed, as the comets became little more than whispers in the vast expanse, astronomers found themselves returning to one lingering question. Why now? Why had 3I Atlas, Swan and Borisov V1 appeared with such expressive clarity during a period when the solar system was shifting so subtly, so quietly, that only the most sensitive instruments and the most ancient travellers could perceive it? At first, this question seemed almost philosophical, but as more data accumulated, it became scientific. Patterns emerged not only in the comets' behaviours, but in the timing of their arrivals. Each comet had entered the inner solar system at a moment when the heliospheric environment was undergoing specific changes. And though their origins differed dramatically, 3I Atlas from the inner Oort cloud, Swan from a fragmented lineage, Borisov from the distant interstellar dark, they all became visible at the exact period when the solar system's magnetic structure was beginning to transition. It was not coincidence, it was resonance. This resonance, scientists proposed, might be the key to understanding why comets behave the way they do. Perhaps certain cosmic conditions, whether solar or galactic, subtly influence the timing of cometary appearances, not through direct causation, but through long-term gravitational nudges, thermal cycles, or even magnetic shifts that alter the delicate balance of forces acting on these distant ice bodies. If this was true, then comets were not random visitors at all. They were timekeepers, arriving when the solar system reached certain thresholds. This idea was so profound that many researchers hesitated to publish it, fearing it would seem speculative. But the evidence grew. Orbital reconstructions, dust grain analyses, magnetic wave models, all pointed to the same possibility. The comets had arrived during a period of alignment between long solar cycles and interstellar pressure gradients. The comets were not merely responding to the environment, they were part of it. This understanding altered the way astronomers viewed the solar system's place in the galaxy. The Sun is not a static star. It moves through the Milky Way, encountering regions of different density, magnetic fields and cosmic radiation. These regions influence the heliosphere, compressing or expanding its boundaries, altering the solar wind, and modulating cosmic rays. Until now, humanity had relied on spacecraft like Voyager to sense the edges of this environment. But comets, fragile, ancient, responsive, could sense these transitions long before any instrument could. One stunning piece of evidence came from studying the faint dust arcs left behind by 3I Atlas. These arcs, at first interpreted as remnants of its fragmentation, were found to align with a predicted shift in the heliospheric boundary that occurred decades earlier. Though 3I Atlas itself had not been present at the time, the dust grains carried echoes of older solar wind structures, patterns imprinted into their trajectories by long-term magnetic fields. It was as if 3I Atlas had inherited the memory of a previous solar cycle and expressed it during its dramatic awakening. Swan's legacy was equally profound. As researchers mapped the fine, particulate debris left behind in its anti-tail, they discovered that the distribution of particle sizes formed repeating bands. These bands revealed a record of solar wind turbulence that had fluctuated cyclically over the course of several months. The anti-tail was not just a structure, it was a graph drawn across the night sky, depicting the oscillations of solar wind pressure. For the first time, scientists had a visual archive of solar wind harmonics spanning weeks, something spacecraft had never been able to capture with such spatial detail. And Borisov V1, as always, contributed in subtle but powerful ways. Its chemical signature, rich with hypervolatile compounds undisturbed since the early days of the galaxy, provided a baseline for understanding how the interstellar environment had shifted since its last passage near the Sun. By comparing these compounds to the ones released during its recent approach, researchers inferred changes in interstellar density that had occurred over tens of thousands of years. Borisov had become a messenger not just of another star system, but of the galaxy's evolving environment. As all these insights took shape, something remarkable happened. Researchers started seeing the solar system not as an isolated bubble drifting through a vacuum, but as a vessel immersed in a cosmic sea. The galaxy was no longer a distant backdrop. It was an active participant in shaping the heliosphere and influencing comet behavior. This shift in understanding didn't arrive with fanfare. It came quietly, through late-night discussions, scribbled notes, revised simulations, and small realizations that accumulated into a profound truth. The universe is not a hierarchy, it is an ecosystem, and comets are part of the connective tissue that binds the solar system to the galactic environment around it. As these ideas matured, astronomers began asking a new kind of question. Not, what did the comets reveal, but what else is the solar system trying to show us? If these wanderers had pointed to magnetic cycles, interstellar pressures, galactic harmonics, what other patterns might lie hidden in their behavior? Could comet tails reveal unseen planetary influences? Could dust streams map gravitational waves from passing stars? Could hypervolatiles record chemical patterns from galactic clouds long dispersed? Could their orbital shifts whisper of dark matter structures we cannot yet measure? Each possibility opened a new doorway. Each doorway hinted at a deeper understanding of the solar system, not as a collection of separate bodies, but as an interconnected organism breathing with the galaxy. Meanwhile, a cultural shift was happening as well. The comets had captured the public imagination not through spectacle, but through subtlety. People found themselves watching animations of Swan's anti-tail, reading about Borisov's ancient ices, revisiting images of 3I Atlas's explosive jets with newfound appreciation. The story unfolded slowly, like a novel written in starlight, and people read it with quiet fascination. For those lying awake at night, listening to the soft narration of these events, the message resonated differently. It offered a sense of perspective, a reminder that the universe is ancient, that change is constant, and that even in the darkest, coldest regions of space, there is motion, rhythm, and meaning. The comets had shown that cosmic transformation is rarely violent. Often it is gentle, subtle shifts in structure, quiet oscillations in magnetic fields, gradual adjustments in the heliosphere's boundaries, and humanity had witnessed it. There was something profoundly comforting in this. In a world full of sudden changes and unpredictable storms, the universe's slow rhythms offered reassurance. A reminder that not all cycles move at the pace of human time, that some unfold across centuries gracefully and without urgency. That change need not be feared. It can simply be observed, understood, and appreciated. As scientists prepared their final reports, they found themselves writing not just about data, but about context, about connection, about the realization that the comets had offered a moment of clarity that extended far beyond physics. 3I Atlas had shown the solar system's volatility. Swan had shown its structure. Borisov had shown its history. Together they revealed its belonging to the sun, to the heliosphere, to the galaxy. And now, as the trio drifted farther into the black ocean of space, humanity carried with it a rare gift, the knowledge that we live in a system shaped not by randomness, but by rhythm, by cycles, by cosmic tides that rise and fall across epochs. The comets had illuminated these tides briefly, beautifully, without warning. And in their fading glow, they left a message etched across the night. You are part of a universe that is alive, not chaotic, not hostile, not indifferent, but evolving, breathing, expanding across time so vast that only the oldest wanderers can record it. And in that realization, something inside humanity shifted too, not loudly, but quietly, like a star adjusting the balance of its own light. As the last residual measurements from the comets faded into background noise, astronomers found themselves standing at a crossroads between what they once believed and what they now understood. The solar system had not changed abruptly. There had been no violent upheaval, no dramatic shift visible to the naked eye. And yet something fundamental had indeed changed, humanity's perception of its cosmic home. The comets had peeled back a veil that had lingered for millennia, and now, with that veil lifted, the universe seemed richer, deeper, more interconnected than anyone had imagined. But what lingered most was not the spectacle of the comets' behavior, nor the scientific revelations that came from studying their movements. It was the feeling, the quiet, pervasive recognition that the solar system is alive with invisible rhythms, and that these rhythms reveal themselves not in explosions or chaos, but in the delicate behavior of fragile wanderers drifting across vast, empty space. In the weeks that followed, the global astronomical community continued analyzing data, each team sifting through tiny fragments of information left behind by 3I Atlas, Swan, and Borisov. Some focused on magnetic oscillations, others modelled interstellar pressure gradients. Still others attempted to reconstruct the long-term cycles that had influenced cometary activity across centuries. Yet regardless of the approach, all paths led back to a single realization. The comets had arrived precisely when the solar system was shifting into a new phase. Not a phase of risk, not a phase of distortion, but a phase of transition, gentle, long, deliberate, a recalibration of the sun's magnetic architecture and the heliosphere's outer boundaries. This transition was something humanity had never been positioned to observe before. For most of history, people lived too close to the sun in time, and too far from the tools needed to witness the larger story. They saw comets occasionally, but not with the detail required to read them. They felt geomagnetic shifts, but without the sensitivity to understand their causes. They sensed the sky changing, but they lacked the language to describe it scientifically. Now, for the first time, humanity could see the solar system's deeper behavior clearly enough to understand its meaning. And that meaning carried a profound sense of stability, because even though the solar system was changing, it was doing so slowly and gracefully, following patterns older than the Earth itself. Patterns encoded into the plasma flow, into the magnetic field lines, into the dust that drifted outward from comets after their fiery encounters with sunlight. Patterns that persisted whether or not anyone was watching. One of the final breakthroughs came from an unexpected source, a graduate student compiling a timeline of the comet's brightest phases. She noticed that the peaks in brightness, not the outbursts, but the softer, slower increases, aligned with subtle dips in cosmic ray influx recorded by Earth-based observatories. These dips, long considered too small to be meaningful, were actually part of a solar modulation wave sweeping outward from the sun. This led to an astonishing realization. The comets weren't merely reacting to solar wind changes. They were responding to cosmic rays themselves. Cosmic rays, those high-energy particles from distant supernovae and galactic structures, were modulated by the Sun's changing magnetic field. When the field strengthened, fewer cosmic rays entered the inner solar system. When it weakened, more slipped through, and the comets, made of volatile ices sensitive to even the smallest changes in radiation, brightened or dimmed in sync with these cosmic tides. This insight completed the picture. Comets were not simply messengers of solar behaviour, they were messengers of galactic behaviour too. They were the only objects capable of tracing the relationship between star and galaxy, the delicate dance between the Sun's magnetic breath and the distant forces drifting across interstellar space. With this realization came a new sense of humility, because the comets had shown that humanity lives in a system shaped by forces far beyond its immediate senses, forces that ripple across thousands of years, forces that shape the heliosphere the way tides shape a shoreline, forces that act slowly, invisibly, yet consistently. And the comets, with their fragility and ancient memory, were the first to feel these forces. And through them, humanity felt them too. In observatories across the world, astronomers reported a familiar feeling when they reviewed the final data. It was not triumph, it was not relief. It was a sense of companionship, a recognition that these icy wanderers, though silent and cold, had communicated something essential about where humanity lives. They had shown that the solar system is not simply a neighbourhood in space, it is a habitat, a place held in balance by magnetic fields, interstellar pressures, cosmic rays and gravitational tides, a place that breathes with rhythms older than civilization, a place that changes quietly, gracefully, across spans of time that far exceed a human life. And now that humanity had seen this breathing, witnessed this movement, felt this rhythm, it could never unsee it. Even casual skywatchers sensed this change. People who had watched Swan's stunning anti-tail sweep across the night felt a quiet nostalgia, as they learned it had faded forever. Those who had marvelled at 3i Atlas's explosions now understood they had witnessed not chaos, but a deep time reaction to an unseen magnetic shift. Those who followed Borisov V1's lonely arc realized they had seen something ancient, an emissary from a region of the galaxy humanity may never touch. And in that understanding came comfort. Comfort in knowing that the solar system does not drift through an uncaring void, comfort in knowing that the galaxy does not exert violent unpredictability upon us, comfort in knowing that the universe communicates its changes not through catastrophe, but through gentle transitions that unfold across centuries. As the scientific world absorbed these revelations, educators, writers, and storytellers began to reshape the way they explained the cosmos to the public. They spoke not of isolated forces but of interconnected systems. They described the heliosphere not as a static bubble, but as a living membrane. They described comets not as icy relics, but as sensitive instruments capable of reading the solar system's pulse. And somewhere in the midst of these reimagined narratives, people began to feel more at home in the universe, because the comets had shown a truth humanity had long forgotten. The universe is not distant, it is present. It surrounds us intimately, continuously, in ways we rarely perceive. Every gust of solar wind, every particle of dust, every faint pulse of magnetic force, a reminder that Earth drifts inside a vast breathing system. As the final analyses concluded and researchers archived the last images of 3i Atlas, Swan, and Borisov, they realized that the story these comets had told was not one of endings, but of beginnings. A beginning of understanding, a beginning of perspective, a beginning of recognizing that cosmic change is not something to fear, it is something to observe with wonder, because the solar system is not a static fortress. It is a river flowing through the galaxy. It bends, it shifts, it adjusts. And comets, those fragile wanderers returning from unimaginable distances, are the ripples that reveal the motion. And so, even though 3i Atlas has dissolved into dust, Swan into mist, and Borisov into the long dark beyond the planets, their message remains. Quiet, enduring, luminous. This universe you inhabit is alive. It is not still. It is not silent. It is not indifferent. It moves with ancient rhythm. and you are part of that rhythm, carried with it through time and through space, a participant in the great unfolding of cosmic cycles, witnessed through the tales of 3 wandering messengers that briefly illuminated the night and then slipped away, leaving humanity changed forever.